Hello everybody, and now you can hear me as well. So, as you can already see from the text that I've written, we are going to look at a module, a KTANE module that was posted by Speaking Evil. This was posted to the community as a manual challenge, which means this is a KTANE module without a manual, and it is up to the community to determine what the rules of the module are. Now, I have not looked at the module at all yet, and I am planning to look at it through a C# decompiler. However, before I do that, I am first going to run the game and take a look at what the module looks like, because we're actually 2 minutes before the time. I announced the stream for 1:15. Well, actually, originally I announced it for 10 o'clock, so I guess in that sense I am late, but I did change the announcement. So for those of you who aren't here yet, let's just quickly take a look at what the module looks like. Okay, so we've got our dynamic mission generator. Now you'll notice that I've already looked at what the module looks like just to make sure that it actually runs in my game, that it works, that it doesn't crash. And here we are. Please confirm that you can hear the game audio and also that you can hear my voice fine and that the volume balance is, if you have any issues, then just let me know. Yes, I'm gonna assume that means it's good. Alright, so what I notice is that we have 4 LEDs in the middle. We have up, down, left, right buttons, and we have some stuff down here, which interesting, the left button is black. Ah, I see. Okay, black means we're on the far left. And then I can scroll through this and I get some characters here. Most of which are these question mark characters, which are used by Unicode converters to indicate that something isn't a character. I also notice these 3-letter combinations, DLE and SI, which stand for let me bring up an ASCII table to show you what I'm talking about. So the ASCII table has these 32 characters at the start, which are identified by some letter combinations. And I notice SI, for example, is number 15. NUL is, of course, 0, as the name implies. And then we have DLE, which, there you go, it's number 16. So we're gonna have to take a look at those. Now, interestingly, this also has quite a few characters, such as this box drawing character and the 3 quarter signs, which are not ASCII. So I'm not quite sure what's going on there, but I have a suspicion. That what this is actually the DOS code page. There we go, 437. It's probably this one, because this one does have the box drawing characters in it, and it also has this there we go, this character here, and the 3/4 fraction. Okay, we have 1/2 and 1/4. I'm sure it is somewhere.
Emergency cleared. All personnel.
I'm just gonna assume it's somewhere and not spend too much time looking for it. Yeah, actually I can't find it. And now I'm suddenly not sure whether this is the right code page. But I guess we'll find this out by decompiling the module. And we'll see what we get. Now, before I leave the game, I'm going to press these up, down, left, right buttons a few times, and I'm gonna see where that takes me. So I'm gonna start somewhere, like here. I don't know. I'm gonna press right. Okay. So that suggests that there is a wall, and I can actually go up. Okay. So I'm gonna put a hashtag to say that this is a square where we can go. There we go. Aha, there is a wall here. We can go right. And there's another wall here. Okay, so I think I'm going to map out the first maze like this. And then we will look at the source code to see if we can find that exact maze somewhere. Okay, there is a wall here. Let's see if we can go up. We can go up, yep. And we can also go right. We can go up again. And we cannot go up further, but just in case there is more maze above that, aha! That arrow just went black, which strongly suggests that this is the right edge. So I'm just gonna assume this is the right edge for now. Let's see, I can go, oh! That suggests that this is the top edge. Okay. Let's see if I can go left. I suspect not. Ooh, but I can. Interesting. And I can go left again. And again. And again. And again. And not here. Okay, I should probably remove the dots in all of the places where I know I can walk. Like, these are all of the steps that I've tried. I'm gonna leave this dot in. In fact, let me change the dots to something that is more like in the middle of the character. Alright, so I believe that I am now here. So let's see if I can go down. I cannot. Can I go down from here? No. And here. And here. Okay, so that means that... Oh wait, I had... Ooh. Okay, that's still a no. Okay, so let's go here and then down left. We are now... Actually, I should check this place. Aha, we can go down from here. And down again. And down again. And down again. And down again, and that takes us to the bottom edge, apparently. Now, I'm willing to bet that there is a wall on the left all the way up. So 1, 2, 3. Ooh, the third one. This one here allowed us to go left, but let's try the rest. So here we can also go left, and then obviously there is a wall there. I already knew that. We can also not go up, so that is a wall. And then let's see if this... Aha, that is also a wall. Okay. I'm going to keep doing this until I have the entire maze, and then we're gonna do the C# decompiling. Alright, there's a wall here, which means I probably want to go here. Now let's see if I can go down. I can go down, and I can go down one more. I cannot go left. I can go left here, but let's go back and try it from here. I can also go left from here, apparently. I cannot go up. I cannot go left. And okay, so that is a dead end. So let's go down here. So now I am here again. I can apparently move down. And I can move left. Here. And left again. And left again. I still haven't found the left edge, so I don't actually know. Ooh, now I found the left edge. I was gonna say, so I don't actually know how big the maze is, but now I know, and now we know that I've figured out about half of it. So let's see, I can go up from here. I cannot go right. Right, let's go back and let's try this. I can go up here. I can also go up here. And not left here, so let's go here. Ooh, interesting, so this is a wall. Okay, let's go here. Aha, so I can go left from here, but I cannot go here. But I can go up. Okay, it's starting to form corridors and stuff. So let's go out of this dead end. So I am now... Aha, I must have made it... No, okay. I did not make a mistake, I just didn't try that yet. Okay, let's go here. That's here. And that's also a dead end. And that's also a dead end. Okay. So let's get rid of that. Okay, so all of this is a dead end. So I'm gonna go down and then 1, 2, 3, 4 to the right, and then up, and then right, and then up, right, up, 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 left. Okay, so we've done this entire part here, and I'm now here. And here I haven't tried left yet, but obviously I would be very surprised if I couldn't go left here, because if I couldn't, it would mean that entire part of the maze is cut off. Hello there, Cool and welcome to the stream. We can go left from here apparently, and not down. We can go left again. Whoops. And we can go down. So let's keep going left as far as we can. Try going down here. Yep, that lets me go down. And then let's go here, and we're on the left edge, and obviously you can go up, because otherwise there would be no other way to get to this square. So let's see if I can go down here. I can. Alright, let's see if I can go right from here. I cannot, that is what I expected. Let's see if I can go right from here. Also no, also what I expected. And this I expect to be a yes. No. Okay, in that case I should check it from the other side. Which is, ooh. Okay, I've lost track. Ah, okay, I just missed one step. Okay, so I want to go left from here, down, left, left. Okay, so I can go here, and that is a dead end. Yes, it is a dead end. Alright, let's go here. Now let me make sure I have the right width of the maze. 1, 2, 3, 4, 5. Yeah, I did get that right. Okay, now let's see if I can go here. Or here. Okay. So I cannot go anywhere here, so I need to go back to this place. Alright, so we go 1, 2, 3, and then we go down. Ooh. Did I... Wait, I thought I was here, and I went 1, 2, 3. Okay, is this one of those modules where you can't press the buttons too quickly? That would be really annoying if that is the case. Let's see, so if I haven't miscounted, I should now be here. And I cannot go left, which means I must be able to go left here, yes. Indeed I am. And then I can go up from here, and I can go left from here. And then of course I can go left from here, otherwise that would be unreachable, and then this is a line. Okay, so now I can safely remove all of these dots, and we can see the entire maze. Well, actually, wait a second. Yeah, I think I'm gonna leave the dots in. Yeah, it's actually more visible, as in more readable, the maze. Okay, so now I'm going to decompile the code and see if I can find this exact maze somewhere. But before I do that, I'm going to write down what's on the on the display here. Let me see if I remember the code for that substitution character, I think is what it's called. No. Replacement, that's what it's called. Replacement character. There we go. It's FFFD. Aha. FFFD. Alright, let's... Oh, it doesn't display it. Well, that's as good as... You know, I'm going to put spaces around it to make it more readable. The second screen says this, and then H, and then we have this, and then we have this. Ah, now it displays these. Okay, whatever. Oh, and there is another... replacement character there. Then we have DLE, close square bracket, and then we have this. Oh, and one more. That is a... Let's see, do I have this? Yep, I do have that. SI, and then this. Okay, that should be all of them. I should also write down the LEDs, which are blue, blue, yellow, white in reading order. And with that, I've written down everything from the module. What are you using for the ASCII? So it appears that FFFD it appears that the module uses FFFD to separate out the characters, yes. However, I noticed there is an FFFD here at the end of the line and another one at the start of the line. In fact, oh, I see, there is one at the start and end of every line, except the start of the last and the end, sorry, the start of the first and the last of the end of the last. Anyway, I'm going to close this down now, and I'm going to look at the assembly and see if we can make any sense of the code. Let's see, I need to find the ID. Right, the ID is, of course, right here. It's this one. And here we have ASCII Maze.dll. Okay, now comes the interesting part. ASCII Maze script. Let's see, in before obfuscated. Yeah, if it's obfuscated, I would be even more motivated to go through it. Is it a plugin of some kind? I see, you're talking about how do I type these things. If you want to install the same program that I use to type some of these things, it's called Unikey. Actually, I should probably link you to this page instead. Right, this is the newest version. But fair warning, it is not a user-friendly program. It is difficult to set up. I'm happy to help you with questions about it, but you know, the first thing after you run it that you should do is type curly bracket HELP for help, close curly bracket, and then a window will pop up with commands that you can use. But that's not what this stream is about. Let's close this. Let's take a look at this code. Now, let's start with awake, because that's what happens when the module starts. So apparently, the first thing it does is it displays one of these sort of emoji strings at random, but I strongly suspect that that's just a sort of welcoming message, so it probably doesn't have any bearing on the rules. Let's see, we have the module ID counter, obviously, and then for 4 iterations it finds me a value between 0 and 7. Okay, so there are 8 different colors, and I'm guessing that these are the colors. So LED colors are these, and they have these values. Okay, so that's the first thing we figured out. And sorry for being late, no worry. Rubik's, welcome to the stream. Okay, so let's see, we have this dot start. Okay, this dot current equals start. Okay, so start sounds like it's a starting position where you begin, but oh, I see, it does this twice. So I'm guessing that start is just a 2-number array which has the x and y position of where you start and where you currently are. Alright. Okay. So if you're at the edge of the maze, then it sets the arrow material to the one that is black, which tells you that we're at the edge. So let's see if, so this has 0 and 6, which suggests that the maze is 7 by 7, and indeed we have 7 wide and 7 tall. So I did get the size of the maze right. This dot maze of 2 times random range 0, 7, 2 times random range 0, 7 equals plus. Interesting. So why 2 times? So it chooses a position with an even x and y coordinate between 0 and 12. Okay, let's see what maze is. Oh! Wait, does that mean there is only a single maze in the no. That can't be right, because there are lots of x's here. Oh, I see. Okay, so this is just a sort of initial string. Right, let me show you what this looks like when you write it down like in a readable fashion. It's actually kind of like a checkerboard pattern, except not quite. So I'm going to change all occurrences of this to this. And then replace everything that isn't an x or a minus sign or a hash. Replace all of these with nothing. 0 occurrences. Why is it not replacing them? Oh, I see, it's because, okay. There we go. Right, and now we want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 things at a time. Put a new line there. So this is what the initial maze, except no, it isn't, because, I should have just done that. There you go. Okay, so this is what the array initially looks like. Here we have these names of the ASCII characters, and now we can see what code page this is. So this has, let's see. So after the ASCII characters, which stop here, del is the last ASCII character, that would be here, this one. So the next one is indeed that, and then that, and then that. Yep, that is indeed what it is. And then after a while, after a set of characters, we get this Spanish ordinal indicator. Then we have the question mark. So I'm pretty convinced now that this is indeed the code page that we're supposed to be looking at. Let's see if it actually has the Greek letters. Ooh, it does not have those Greek letters, and it does have the 3/4. So it is similar to this, but not quite. So maybe, wait, let me think. If it has the 3/4 thing, but not the, let's see, code page I think there was one with an 850. I think it might be that one, although I thought... Aha, I thought this one didn't have the box drawing characters, but clearly it does, and it does have some extra letters, it does have the 3/4, so I think this is the correct code page that it uses, because after the 3/4 we have the paragraph sign, and then the section sign, and then the divide by sign, then the cedilla, then the ordinal, the degree sign, the diaresis, the middle dot, the superscript 132, for some reason in that order, I don't know, then the middle block, and then the non-breaking space. Right, so it is actually code page 850 that we're dealing with. So let's write that down here. Okay, now back to the code. Let me actually put that here so I can access that. Right, so this is where we were. Oh, there's a Twitch help message. So it already has Twitch support, which allows you to cycle between the displays, move around the maze, activate colorblind mode, submit and reset. Okay, so there is a submit button. I didn't really notice a submit button. Maybe the LEDs are clickable, maybe the screen with the characters on the bottom is clickable. Oh, no, I remember there was a green sort of target on the module. In fact, I can just look at it, show you here. Right, this is probably the submit button, and this is probably a reset button. Given that it says reset here, I'm going to assume that's a reset button. Alright, let's go back to this awake method where we were. So here, so we set all of the even indexes to pluses, which means that we end up with, wait a second, that's all of, it sets all of the ones that are currently minus signs to pluses. That is very strange. Okay, so all of the minuses become pluses for some reason. Alright, now we have an infinite loop here, and I'm going to bet that this is probably a maze generation algorithm, but I'm going to go through it and see if I can make sense of it. Let's see, I do want that. Yeah, Goofy, the thing is, if you put while parenthesis true, then the compiler generates code where this and while true is indistinguishable. So it's entirely possible that this is not obfuscated and this is just what while true looks like in the decompiler. Let's see if there are... Okay, so it doesn't set all of them to plus, it sets any random one of them to plus. So for example, this one here. Okay, let's see, if there aren't any minuses left, then break. Then we have an array of 2 values with random coordinates, so that's probably just a random place in the maze. And then while that is not equal to a plus, okay, so it tries to find a plus sign somewhere. Oh, this is not how you do that, but okay. Okay, so now we take right, so this is probably a direction, up, down, left, right. Let me untangle this thing. I'm just going to put some new lines in there to make that a little more readable. So while num equals 0 and all of that, or, right, let's do it like this, there you go. So while num equals 0 or that, num equals 1, num equals 2, num equals 3, okay. So I'm gonna bet that these are the 3 different directions, and indeed 0 and 1 check whether we're on the so if this is the y coordinate, then this checks whether we're on the top edge, this checks whether we're on the left edge, and then this is the bottom edge, and then this is the right edge. Right, so if we are already there, then this is fine. Or if there's something other than x, I see. So x means that we haven't visited it yet. I keep pressing Alt-Tab when I mean to switch tabs here. Or, okay, minus. So x and minus both mean we haven't been there. Completely unrelated question, but can you make compounded logic if... I don't understand the question. So let's see. So it always uses 2 times, right? Which means that the even indexes here are where the walls would go, right? And in between those are the cells where you can walk, right? And then the odd indices are where the perpendicular walls would go, and you can never be on those spaces. So if you're on this space, for example, and you go right, you would end up here unless there is a wall in between. This is how he has set up this array. Alright, so switch num. So depending on, oh, I see. So this while loop tries to find a new direction that you can go to. Although it doesn't seem to check whether there is any direction that, like, what if there isn't one? Oh, we'll find out. So if 0, then we're trying to go up. So, alright, it uses the slash character to mean we've been there, and the plus character. So in this case, so let's say we're here, and we go up. Then it would set this to a slash and this to a plus. Ah, okay, I see. So slash here means that this is going to be a wall. Right. And then, yeah, so it always sets the adjacent square to slash, and then one square further in that same direction to a plus. So that way it will gradually change all of the minuses to pluses until it has filled the entire maze. And then the slashes will be the walls? No, the slashes will be the places where you can go. Right? Because, yeah, I think that's it. Slashes will be the traversable places, and X's will be the intraversable spaces. Yeah, so as soon as we've gobbled up all the minus signs, there will still be some X's left. So that's probably what happens. So let's see. What does it do here? It goes through all of the even X. I'm going to assume that this is X coordinates, this is Y coordinates, because it uses those to index into this maze. So, you know, the decompiler doesn't know what to make of these variables, so it does its best guess. Okay, so if we encounter a space that has... Oh, I see. So this is how it prevents itself from getting stuck in a dead end. Right, so let's say we're here and we've already done the up, and we've already done the right, and we've already done the down, and we've already done the left. Then it would look like this. So how does it stop itself from choosing this again and then, you know, get stuck in this loop, trying to find a direction that it can go to? The way it does that is it goes through the entire maze after this first step and finds dead ends. Right, all of this checks whether there is a plus where, right, let me turn this into a more readable line as well, so you can see this. Right, if this is a plus and this, and this, and this, and this is the case, and now you may remember that M2 was actually a Y, and N is actually an X. And then you can easily see that what it is doing here, it tries to find a plus where all four directions, right, the one above, the one to the left, the one below, and the one to the right, sorry, this one is below, this one is to the right, are slashes. Wait a second, it does allow a slash. Oh, I see. Yeah, okay, so for any plus place where any of these are still the case, you do have a slash. Wait a second. So on the left side, okay, so if it is a plus and we're on the left side, or there is a slash to the side, or there is no, okay, so that, right, okay. So it checks for all four directions that there is a slash and then something other than a minus sign. Right, if either of those two cases, I mean, it's always going to be both because it always sets the slash and the plus sign, but it seems to check both of them and it just accepts either. So it will always just stop at the slash Right? If this is ever false, then the other one is also going to be false, but it doesn't matter. So if it finds any plus sign where all four directions have this, then that is a dead end, and it will change that into an O, and so it will no longer consider that position as one that you can move from. So this is indeed the same maze generation algorithm that I have described on the stream before. I'm happy to, maybe one day I should make a YouTube video on this so I can refer people to, like, here, this is the sort of standard maze generation algorithm to be used for puzzle games such as KTANE. Right, except that this one here uses a character array in a creative way, but it works just as well. Okay, so then it selects. Let's see. So maze is a string array. So it takes. Okay. It changes everything to an X that isn't one of those characters, and everything else to a space. Right, okay, and then presumably if you then output it to the log, which the plan is probably to output this to the log once you're done with the manual challenge, so then it'll be a totally reasonable looking maze, because it will have, let's see, if it doesn't contain. Yeah, so all of these things that we've set to slashes and pluses, they will be traversable, so they will all become spaces, and then everything else will be X's, and these X's will form all of the walls. This is really cool. This is, yeah. Okay. And so now we use the plus sign to indicate the position we're in, because remember that start is the place where we decided where we would start. Okay, so we set a plus there. Now what is this? So 8 times we go through all of the coordinates. 8 times, interesting. If there is a space and... Okay, I'm going to... I have no idea what's going on here, at least not yet, but I'm going to unravel this part of the code. Let's see, I'm willing to bet that this is where it repeats. Yep, there we go, this is the repetitive part. Repeating part, excuse me. Okay, so if we find a space anywhere, and this time num3 is the x-coordinate and num4 is the y-coordinate. So if we find a space anywhere, and I'm just going to make this bigger so you can read it. So if we are not on the left edge, sorry, on the top edge, and there is not an x above us, which is a wall, and this is a plus, which means, okay, this checks whether we can move in any direction at all. Wait. So what this does is it finds all of the places that we can move to, right? It will find all of the places that have a space in them, and are one traversable place that could be a wall away from the plus, but not with a wall in between. Remember, the x's means that there is a wall. So if there is not an x, then this can be traversed, and the plus is our current position. So it's, if the plus is on the other side of that character, then that is a place where we can go. So it marks all of the places where we can go with a minus sign. And then and then it wait a second, it changes the plus where we started to an O. Yeah, if this is a plus, it changes it to an O. And if it is a minus sign, then it changes it to a plus, which means that, okay, so we start with this, right? Let's just pretend that we've done this, right? So let's just change all of the minus signs to x's. So obviously this is a bit full right now, but what it will do is it will put the plus on the start position, and then it will check all of the directions to see where it can go and change those to minus signs. That goes here, 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 and here. And then it will go through everything and change the pluses to O's and the minuses to pluses. I'm not quite sure yet why it does that, but I suspect that it's trying to figure out in a loop. Yeah, that's probably why it does this 8 times, or maybe not. So it's trying to find out all the places where we can go. Well, given that it specifically does this 9 times, like why 9? 9 is a weird number. I kept saying 8, but obviously it's 9. It goes from 0 to 8, but it's 9 iterations. So it will do this 9 times, which means that it will find all of the places in the maze that are 9 steps away. Like exactly 9 steps away. That's very strange that it would do that. Let's see, a string text equals, now it gets interesting. So what do we do here? Yeah, I think this just puts the maze together into a single string. This dot exit. Oh, okay, and now it chooses. Wait a second. Okay, so once again, this is a random coordinate, and we have 2 coordinates, x and y. And so the exit is decided at complete random if not text contains space. Okay, so it okay. So it decides on a random position of the exit, but then if the position of that exit is not a space character, then that means that it is more than 9 steps away. So it will okay. So it will keep deciding on a new exit, but this time it will only make sure that we are less than 6 away in sort of in space, regardless of walls that may be in between. Whereas if it does contain a space, right, let me examine this a bit more. What is this exactly? So we take the maze, and then for each array in the maze, which is a row, we look at where, right? We just look at the what's it called? The even indexes, right? And then we turn that into a string. And then we take the even rows and turn that into a string. Yeah, that's literally just, so all that does is it just takes the the even index characters, which in this case would be the plus and the O, but not the spaces in between where the walls would be, which makes sense, right? It doesn't care about the walls, it cares about all the places that we can reach or not reach. Okay, now I get it. Okay, it's not checking whether we're within 9 spaces. It wants to make sure that we're at least 9 spaces away. So it marks all of the spaces that are 9 steps from the starting position with pluses, right? And then it chooses an exit position at random, and if that is no, wait. It checks this entire thing. Text contains the entire maze. Why would that not contain a space? If it does not contain a space, then that would mean that the entire maze is reachable in 8 steps from the starting position. If that is the case, it will just choose an exit position at random that is less than 6 sort of positions away in the maze in 2 dimensions, but regardless of the walls. But if there is a space, which means there is a place that is more than 9 steps away, then it will just find a random exit that is not O. And remember, O was, yeah, that's right, all of the ones that are exactly 9 steps, so not exactly, that are within 9 steps away will be O's, because, right, it uses the pluses in the first step, but then it changes all the pluses to O's before it moves on to the next step. So what ends up happening is you'll have pluses in all the spaces that are exactly 9 spaces away, and O's in all of the places that are less than 9 spaces away. This is very interesting. Okay, so we do another transformation here. We change all of the X's to these square characters, and everything else to filled in squares. Oh, I see, there's a knot here. Okay, so all of the walls become filled in squares and everything else becomes empty squares. And then we assign that to maze, which means that this entire calculation here about the distance was only made to decide on the exit. So this is not even relevant for the rules of the module, right? The rules of the module don't need to know how it decides on the exit, only how the expert can determine what the exit is. Right, anyway, so we set the start position to an S, the exit to an E. That makes sense. Ooh, I see. Bin string. Oh, that name is a total giveaway. Right, this is a Boolean array. So what this will do is it will encode the start position and the exit position in binary in some way. Yeah, that's right. You see, because the maze is 7 by 7, right? It could have been 8 by 8 really, but it's 7 by 7, which means that the x-coordinate and the y-coordinate can be encoded in 3 bits, right? And you will notice that it uses indeed 3 statements here to encode the start position and then 3 more to encode the exit. Alright, so now we have a 6-bit binary string where the first 3 bits give me the starting position, and the 90th, 91st, and 92nd bit gives me the exit. And now we have something called int. Let's see what this is. That is an integer array that was randomized here. Oh, that's the LEDs. Yeah, that's right. That was the LED color. So let's go back to this. Now, I don't know if you noticed this, right? But it seems that everything comes in groups of 3s, right? This comes in groups of 3s, this comes in groups of 3s, and something else comes in a group of 30, so that 3 times that gives you 90. This is interesting. Okay. I see what's going on. Okay, so what this is doing is, depending on the colors of the LEDs, it will flip some of the booleans. Hello there, Red Penguin. Welcome to the stream. Okay, so what this does, right, is it takes the first 2. Well, actually, not the first 2. It takes the first and the fourth LED, but there are only 4. Okay, let me check this again. Oh. Right, okay, 0 and 3 gives me the first and the fourth. Okay, so this is the first and the fourth LED, right? And it checks whether the most significant bit of these is set. Wait, how many colors are there? I thought there is only... Yeah, there is only 8 colors. Oh, I see, it's divided by 4. Right, so every LED color is going to be a 3-digit binary number, right? So for example, 0, 1. 0 would be 2, and therefore green. So what this is doing here, divided by 4, is it shaves off the least significant 2 bits, and it finds me what the most significant of those 3 bits is. Right, so if that is set, then it will negate or flip 3 bits, namely these 3, the 3 that make the exit. Okay. And then, okay, so if the top bit is set, it will scramble the exit. If the second bit is set, it will scramble the, right, this is also the exit. Yeah, this is also 90 times, so that, yeah. Oh, I'm such an idiot. Okay, num9 Goes from right, okay. So in the first iteration, all of this changes the start position, and in the second iteration, it will change the exit. I should have realized that much sooner. That was kind of dumb. Right, okay, so it will binary negate the start or end position depending on whether 3 times. Okay. So the top left, right? So the top left LED tells you whether the start position is scrambled, and the bottom right LED tells you whether the exit is scrambled. Except that we haven't looked at this part yet, which oh wow, why is that here? 3 to 6. No. This? Because, okay, we started with an empty binary string, right? This was all set to... Let me see where else this variable is used. Yeah, this is the first use of it, so it starts out with all false. Okay, so only the first 3 bits, and the 90th, 91st, and 92nd will have any information in it. Okay, I see. So this for loop is for the x and the y coordinate. So the first 3 bits give me the x coordinate, the next 2... Okay, right, now I have something here. Okay, so bin string. Bits 0 to 2 is start x. Bits 3, 4, and 5 is the y coordinate of the starting position, and bits 90 to 92 is the exit x, and bits 93 to 95 are the y coordinate of the exit. Okay, right, and now the x coordinate of the start position is scrambled if the, let's see, okay, so this scrambles only the x coordinate, this scrambles all of them, and this one here looks at where the exit coordinate is and swaps. It swaps the x and the y. Okay. So, let's see. The top left and bottom right indicators. Rather LEDs. I'm gonna call them LEDs because indicators already mean something else in KTANE. Yeah, so this number here is either 0 or 1, therefore this will be 0 or 3. So it's the first and the fourth. Yes, okay. So if bit 4 is set, then start x is negated. If bit 2 is set, then I'm still a bit confused by the fact that it seems to... okay, so the top left LED determines whether the start is scrambled. The bottom right LED determines whether the exit is scrambled. And within these LEDs, if the bit 4 is set, then the x coordinate is negated, and here it is all negated, which of course may cancel out with this one. And if bit 1 is set, then x and y are swapped. Okay, that is what I gleaned from this. I think this is correct. Now, let's see, we have another loop that goes through the numbers from 0 to 6. So it has 7 iterations. And then here we create an array. So this is the top right indicator or LED. Let's see what the top right LED does. I'm kind of bothered by the fact that I'm lowercasing that. I'm going to uppercase this as the word LED should be. And let me also put this in this document. And let's get rid of this. Let's paste this here, and let's actually save this somewhere. puzzles, KTANE, let's see, KTANE ASCII Maze challenge. Let's save it there. Okay, so let's see what the top right LED means. Okay, so we create an array to determine the 3 bits that the LED's number is based on, but it's in a scrambled order. You see this? This is the middle bit, this is the most significant bit, and this is the negation of the bottom bit. Actually, no, those two are negated. And this is the bottom bit. And then this is whether or not that is whether or not the coordinate we're looking at is even or odd. So let's see. For each other coordinate from 0 to 6, okay, so now it will use the rest of the ASCII characters to encode the rest of the maze. Right. You know, it's kind of interesting because this whole time that I was looking at the maze generation algorithm, it never occurred to me that having done this on the module was completely pointless. Because if the module generates a new maze every time, you know, then obviously this will just be different from any other time that you run the module. Okay, so let's see what's going on here. So we now know that this binary string has these bits, but obviously there is a big gap from 6 to 89. How many bits is that? That's 84 bits, which if I divide that by 4 is 21. Now, why would I divide that by 4? I want to divide that by 3, don't I? Well, let's see what else happens here. So 6 times that number plus that number plus 6. Okay, so that plus 6 indicates that we're starting at bit number 6, right? So let's see. Oh, wow. 12 minus... Okay, so this num13 thing is an x coordinate, right? We know that. Right, at least I think I know that. But here, it sometimes flips the x coordinate, so the maze may be horizontally, what's the word? Mirrored. Right, so this is the normal coordinate, and this is the reversed coordinate. And then we check this weird arrangement, and if that is the case, then we flip the vertical coordinate. But wait, why does the vertical coordinate only go up to 6? Like, why are we only encoding 6 lines? Oh, I know why. Because what all this does is it only tells you what the horizontal walls are. Of which, right, let me show you this. This is really cool. So, you might have a position that you can go to here, or here, or here, or here, right? So in each of these sort of even places, which means that all of the horizontal walls are going to be in this line, this line, this line, and now let's count how many there are, and you will see that it turns out there are in fact 6 of those. And now for the vertical walls, the exact opposite is going to be the case, because the vertical walls are all going to be in these lines, which of course there are 7, but then they are going to be in these columns, of which once again there's going to be 6. So that's probably what's going on here. So we've now figured out that bits 6 to, let's see, 7 times 6. So there are 42 bits that tell us what the horizontal walls are. Plus the 6 bits, of course, so it's 48. So 47, so 6 to 47 tell us the horizontal walls, and the rest very likely the vertical walls. And then we'll need to figure out how the top right and the bottom left LED mangle these. But let me just very quickly make sure. Yep, I got the 48 right, and this is Ah, okay, so they are always in reading order. That is good to know. Actually, let me make sure of that. This, I need to know if this is an x or a y coordinate. It is an x coordinate. Yes. And this is the y coordinate. Okay. So as I said about mangled, it turns out they're never actually mangled. They're just it. It's just sometimes mirrored or flipped. Yeah, that's what that is. Okay. So I'm still not 100% certain that they are in reading order. So I want to figure this out. So the x coordinate goes from 0 to 6, obviously, and then okay. If these are the x coordinates and that's the outer loop, and then in the inner loop we do the y coordinates. So these are actually vertical. So these go in columns. Yeah. So the horizontal walls are represented in column order, and the vertical walls. Let's see about that. Well, this array goes. Sorry, this for loop goes to 7, and this one here goes to 6, which strongly suggests that this is still the x coordinates, and indeed this is also used in the first index here into Maze, and then this num16 here is used in the second index. So that is the that is the same order as before. Okay, so with that, okay, so now let's figure out what these actually do. Okay, so let's see. This is horizontally flipped if it is horizontally flipped if this is false. And this is false if that is equal to 1, which is the middle bit. So top right LED bit 2 is set. Okay, and it is vertically flipped if this is the case. Right, what is this? Let's see. Okay. Just out of curiosity, when you see this code or any code, do you sometimes think things are overly complicated? Oh, that's a very interesting question. I mean, it depends. I mean, sometimes, if the code is simple enough, I'm going to take this opportunity to pour myself a drink. If the code is simple enough, then it is sometimes possible to be reasonably confident that it is as simple as it can be, that it cannot possibly be simplified. If the code is medium complexity, I might sometimes be able to think of some simplifications that might just, come to me due to my experience with programming. But if the code is very complicated, which this one here certainly is, then this is definitely not obvious how the code could be simplified. In particular, the specific way that the author has chosen to represent the maze in memory, which is as an array of strings, and strings of course are kind of like arrays of characters, so it's kind of like a 2D array of characters, is not something that I would have done if I were to implement this, but who am I to say that it's the wrong way, So it would just be a different way, and I would just have to adapt. It is good to have apple juice by my side at all times. Okay, so let's see. We're looking at these 3 things here. And so saying not and then XOR is actually the same as equals. Okay, that's just logically the same. And this here says that the top right LED's 4-bit is 0. So if I negate both sides, right, okay, so top right LED bit 4 is equal to not that. Right, now this is saying that the bottom bit, bit 1, so that is top right LED bit 1, is set, and that. Now this says the x coordinate. Oh my. Wait a second. the x coordinate is odd. Okay. So it is actually quite scrambled. So that means that every, like for example, so this column here obviously has an even. This explains why he did 7 by 7 instead of 8 by 8. It's so that, right, it's so that you can swap, right, so this is 1, 2, 3, 4, 5, 6, 7, right? It's so that you can safely swap this with that, this with nope, no, wait, I'm talking nonsense. Yeah, anyway, so he does actually swap this with that, and then this with that, and then this with that. Right, so what's actually going on is that if you see, if this column here is swapped or not is irrelevant. But yeah, so what was the condition here again? It was x coordinate is odd, the zero-based x coordinate, that is. And if that is odd, so that means that this column and that column is always swapped. Okay, and nothing else is swapped. I mean, this one here will be swapped with itself, but you know that makes no difference. So now, as I say this, it turns out that that it didn't actually matter. No. It does matter. So here. Okay, so here's the thing. Yeah. Okay, so this is why it's not 8. This is why it's not 8. This is why he needed an odd number. Imagine it was 8, and you were to swap these and these and these, and then also these, right? Now notice what you're swapping. You're swapping something that is even with something that is odd. And then here you're swapping something that is odd with something that is even. So what this loop would then do is it would decide that one of those two needs swapping with the other one, but that one doesn't. And then what you end up getting is that one of these columns replaces the other column, and the other one is discarded. So you get 2 copies of the same column, and 1 column is missing. So you can't do that because it wouldn't have all of the information in it. This is why he used an odd number of. This is extremely clever. I'm very impressed. This is amazing. Okay, so if the bit 4 is equal to, let me just absolutely make sure I got this right. If the bit 4, which is this one here, right, is equal to, yeah, now I'm confused because there is only one not, and I use that to turn the x. So I need to be sure of this, so I'm just going to analyze this a second time. So we said, first of all, these parentheses are redundant, and this is just the code to swap the coordinates. So this is the actual expression, and if I remove the not, then XOR turns into equals, and then this array 2 of 1 is this one, so that says whether the bit 4 is equal to 0. Okay, this is what's going on, right? I put the not in front of here to compensate for that. Right, so I can just do this. Okay, now I'm convinced that this is, let me just very quickly look at these. Right, the LED bit 1, that is indeed what this is. And then this checks whether the x coordinate is odd. Yeah. Okay, this is extremely clever. So what this ends up doing, right, is it tells you, so this one essentially tells you whether the whole thing is flipped or not, and this one tells you whether every odd column is swapped. So I'm going to have to unravel this later to extract a set of instructions for the expert, but for now I'm just going to write it down like this. And now for the vertical walls, let's see, this is exactly the same as this, and but now... Oh, but now look at this. This now uses the... Oh, so everything that I said about the odd number of columns and rows is irrelevant, because here it uses this on the x-coordinate when dealing with the vertical walls, of which there are only 6 columns. So let me see what this... Here, it does actually change that number. I am a bit confused now. Knowing that decompilers exist, that the coding is dictated with that in mind. I don't think... I don't know about Speaking Evil, but I don't think any other modder has done that with decompilers in mind. I think with all the other manual challenges, it was kind of tacitly understood that you just don't use decompilers to tackle these challenges. Okay, so... Right, let me take a quick look at this. So we're looking at these bits. Okay, now if... So this is the middle bit once again, right? So yeah, here you are. Well, that's because I set myself the challenge, not the author. So this is horizontally flipped if the bottom left LED bit 2 is set, and it is vertically flipped if the bottom left LED bit 4 is not equal to the bottom left LED bit 1. And now this is very, very odd that it will use that. Let me just very quickly look at this. Yes. Well, I'm really confused by this, but I'm going to try and deal with it. Oh, wait a second. Yeah, no. Okay, I'll try and figure this out later. Okay, so now what else do we do? Ooh, there is even more going on. Let's see. Okay, so for every value from 12. Where did we see the number 12 before? Like, why would it be 12? Ah, that is 2 times 6, and 6 is the number of wall columns or wall rows. And then we have 8, which is of course... Ooh. Okay, so bit string of 8 times that. So by the way, I should probably do another calculation here, which is that, remember we had this, right? This is exactly 42 bits. So what if I go forward another 42 bits? I get 90. Okay, so we have actually filled all of the bits. Yeah, for a moment there I wasn't sure if there's another gap between this and where the exit coordinate is encoded. So apparently there isn't. Right, let's see. What is this doing? If... Oh, I see! This simply turns the bit string, the binary string, back into numbers, which it does using mathf.pow, which it really, really shouldn't. Really shouldn't. But let's hope it works properly. And then it does this. Aha, so the first bit is the most significant. Yeah, that makes sense. Okay, and then it just sets that character to the, the character from this table, which is actually code page 850, and not ASCII. So det chars, I'm gonna assume, is the displayed characters. I don't know why it's called det. Let's see. Display list. Okay. Okay, so our theory was correct, that it takes these characters and joins them with these separation characters in between them. So let's see. Where string x int y. So for each character, okay, let's see. So we've got... Okay, so what this does, right? Okay, let me just very quickly make sure that I understand this. So we have 96 bits in total, right? And 96 is, of course, 12 times 8. So what this is doing, this is why there is a 12, is because it can subdivide these 12, or rather these 96 6 bits into 12 bytes, and each byte, of course, has 8 bits. So det chars is actually the bytes. And then what we're doing here is we're taking... Oh, I see. All this does is it just takes a slice out of this det chars thing. So for each of those 4 screens, right, because this is going to be 12 characters, it's going to take 3 characters at a time, and that way you split 12 characters into 4 screens of 3 characters each. So that's why there is a 3, right? So for the first screen, where I is 0, this is between 0 and less than 3, so 0 and 2, so it's the first 3. And then for the next screen, it goes from 3 to less than 6, and then from 6 to less than 9. Welcome to Timway being amazed by everything. Well, I'm still not entirely sure how the vertical flipping there works. Okay, so all this does is it just simply, literally just outputs the bytes. Alright, starting position. Oh, it actually logs the starting position. I could have just checked that in the log. Okay, so now that we know how the starting position is scrambled, let's do something. Okay, let's do something with the module that we had. So we know that the top left LED, alright, let's get rid of this. The top left LED was blue, which is 1. So top left, let me do this, top left is 0, 0, 1 in binary, which means that the bit 1 is set, so X and Y are swapped, but the other two are not. Alright, now the bottom right LED is white. Okay, so that means that the start position has X and Y swapped. Now the white, of course, is 7, which is all of the bits set, so 7, 1, 1, 1 in binary, which means that the exit has X, Y swapped, and Y negated. Right, because if you negate X and then you negate both, you end up with having only Y negated. But then X and Y are swapped. Okay. So, this means that I should be able to use these characters that I've written down here to deduce what the starting position was, which, if I'm not mistaken, was somewhere around here, somewhere in this vicinity. Alright, let's see if we can do that. So the start position consists of the first 6 bits. The first 6 bits are, of course, the first 6 of the first 8, right? So this first character is an E with an excuse me. It's an E with a grave accent, which we can see here has this code page value, which of course in binary, bless you, thank you very much, which of course in binary we can use the programmer mode here to convert hexadecimal E8 into binary, which is this, right? And then out of these, that and that will be part of the starting position, and this here will be the beginning of the walls thing. So that means now the start position only had X and Y swapped, which means, well, because this is 7 and this is 2, that would mean that the X coordinate was 2 and the Y coordinate was 7. Well, that was definitely not the case, because I remember that we didn't start on any of the edges, right? And besides, 7 can't happen, right? The start position has to be between 0 and 6. So maybe there's something else that I missed. No, this is, okay, well, that's very interesting. So if my understanding of this so far is correct, then 111 should never be possible among the first 6 bits. So that is very surprising that this happened. But let's take a look at the exit coordinates. So we're looking for bits 93, no, well, actually 90. Okay, so we want to skip 11 bytes, right? If we skip 11 bytes, then we'll be at bit 88. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, all right, that adds up. So this obviously is, I shouldn't say obviously, but it's BB. Okay, so what's BB? BB is in fact this. Right, this time we're discarding the first 2 bits because we're looking at the last 6, right? So I'm just gonna put this, there you go, because we don't care about those. And then this and this. Now this time the exit position has all this. Right, so the first of all, x and y are swapped, which means that this is the y value and this is the x value, and the y value is negated, which means that that would have been a 0 and that would have been unaltered. But unfortunately we can't verify that now because I closed down from the game, but we can, can we verify this? So what I can do is I can look at the log file, because I was going to do that anyway. I can look at the log file to see what the start and exit positions were actually. In fact, let me see what the thing here. Yeah, it genuinely finds. Oh, wait a second. This is actually. I thought this was the y coordinate. Aha! See, this whole time I was assuming that the first coordinate is the x coordinate and the second one is the y coordinate, and then I deduced that the order in which it decodes the walls is in column order. But that was an assumption on my part. It could be that in this array the y coordinate is first, which makes sense because it's an array of strings, and if every string is a row, then the first index tells you what row it is, which is y coordinate. So it should actually have the y coordinate first, which means this is not in column order, this is in reading order, which is sensible, and that means that the actual starting position was to, well, okay, it still can't have been 7 though. Alright, now let's take a look at this. The starting position was Charlie 5 and the exit is Alpha 3. Right, Alpha 3. No. No. Alpha 3, it should. Oh, gong. Oh, blah, blah, blah. Okay, so it will use the number 1 to indicate a coordinate of 0, which means that what I got here was alpha 4. So why would it be 4 instead of 3 is what I wonder now. And also the starting position is supposed to have been Charlie 5. Now this is indeed Charlie, but this is not a 5. So let's figure this out. We can figure this out. I'm absolutely certain that we can figure this out. Okay, so this character is echo 8. Right? Oh my gosh, I'm so dumb. This is the Unicode value. I should have realized that because I noticed that with the non-breaking space. No, the actual code page 850 value for that is 8 alpha. So I was just looking at the wrong encoding the whole time. So 8. Right, let's just do this again. So 8 alpha, of course, is 1, 0, 0, 0, and then alpha, which is 10, would be 8 plus 2, kappa //, and then here we want to discard those last 2 and take these 3. And this, ladies and gentlemen, so start has x and y swapped, right, which means that the first one, which we initially thought was the row, would now be the column, and then this gives you 8, which would be, wait a second. What did it say? It said Charlie 5. I'm still not getting a Charlie. Let's see. So this is... Oh, no. It's not an 8. It's a 4. And this is a 2. Right? You add 1, you get 5, and 3 is Charlie. We get Charlie 5. Ladies and gentlemen, the starting position is Charlie 5. We understand the starting position. Now, let's do the same with the end position. I can do this, I can do this, I can do this. This is the character that it was. Is it? Yes, it's the right pointing one, which means the code we want is Alpha Foxtrot. We want AF. Now, A is 8 plus 2, and f, of course, is this, and we care about these groups of 3, which means this is the value 5, this is the value 7, and we know that the y-coordinate is negated. So one of these is negated. Let me make sure that I understand which one. So it had x and y swapped, which means that normally the row comes first, but now that would mean that the column comes first, so it's like this, and then y would be negated. And the negation of 7 is 0, so we're looking at Foxtrot 1. Yeah, that's not what we had. We had alpha 3. Right, okay. Okay. If both of them were to be negated, then I would indeed get a 2 here. Right, okay, so the negated values would be 2 and 0, right? If both of them were negated, then this would give me a 3 and this would give me an alpha. And that would give me alpha 3. Because, you know, they're also swapped. Now, let's figure out why both of them would be negated. Let's go back to the code, not the chat, the code. And let's find out if I can figure out, figure out if I can find out. Right, so, here, let's see. Where was the code that did the mangling? That was. Is that no? This code just decides on the exit. This one here puts the start and exit completely unaltered into the bin string. And then this is where the mangling happens. Okay, so for the top left indicator, if the 4-bit is equal to 1, then we negate the first coordinate, which we now know to be the y-coordinate. All right. Yeah. So in our case, then, right. Let me just read through this. Okay. So if the 4-bit is set, then we scramble the first coordinate. If the middle bit is set, then we scramble both coordinates because we go through all. Oh, it starts at 3. Oh, it starts at 3. So so actually this just says x negated. That's what's going on. Okay, so that means x and y are. Okay, we figured out, ladies and gentlemen, we figured out why both of them are negated here. So now we understand the exit. All right. Now for the start position, we had this, which was this, which is 8a. Yep, that is correct. Which gives me an 8, which is this, and then an a, which is this, and then we don't care about those 2 bits, we care about these, and then that would be normally the y value and then the x value. And now our top left LED says the top left LED was of course blue, which is number 1, which means the bit 1 is set, so they're merely swapped, and that means that this is actually x and this is actually y. The x coordinate is 4, which is echo, and the y coordinate is 2, which is 3, echo 3, but I didn't have echo 3, I had Charlie 5s. Okay. Right, so that means that, okay, you know, if I do it like this, then I do get Charlie 5. Hello Mark Sam, welcome to the stream. Okay, so now, okay, so if I'm not mistaken, so my evidence suggests that x is normally first in the bit in the bit representation. Look at that! Yes! Okay, I figured it out. You see, this actually swaps the 1 and the 0. Okay, so it does actually encode x first, and then y, and then it applies the LED. Yes, okay, we've got it. We've done it. Okay, now I want to see if I can decode the entire maze given the rest of these characters. I want to see if I can do this entirely by hand. And here we go. Okay, so I don't care about the start and the exit anymore because we figured these out. So I'm going to write down all of the hexadecimal codes for all of these characters. So for the first character, which we've now looked up a million times, we know is 8A. The next one is null, which is 0. And then we have the character 9. For the ASCII characters, I can use Unikey to determine these. Then we have a capital H, which is 48. And then we have that box drawing character going in the corner like this. That is Charlie 9. And then we have this kind of box drawing character, and that is Charlie 3. Excuse me, that goes here, please. Then we have DLE. So we need another ASCII table for that, because I don't remember where DLE was. DLE is number 16, which in hexadecimal is 10. Then we have the close square bracket. I think I can do this. Yep, I can. That is the close square bracket. And then we have this character, which we want to look up here. That is in Charlie Alpha. Then we want this 3/4 fraction, which is Foxtrot 3. Then we have SI, which I need to look up here. That is 0 Foxtrot. And finally, we have the right-facing Guillemette, which is Alpha Foxtrot. Yep, we already had that. Okay, and now I need to turn that entire thing into binary. Now, fortunately, I can relatively easily do that in one fell swoop by just taking this and putting it in this website, which in my experience can do quite a lot. So if I just turn that into binary, that just literally dumps me all of the binary code right here. Wait, no, that is not long enough, is it? This has a length of 58. Yeah, we expected 95, so it probably can't do all of that. But that's okay, because we can literally split this up any way we want. So I'm literally just gonna, let's just do that, and convert that, and hope that that is enough. So what I just did is I did 12, so 12 times 4 is 48, so I expect this to be 48 characters, and it is 48 characters. So now the other 12 would give me this, and here we go, and then that gives me a total of 93. I wanted 96. Alright, so how many is this? This is also 12. Why am I... Oh, of course! Oh, of course, it just removes leading zeros, that's why. That makes total sense. You want the first one to be a 1 and then a 0, right, so this is actually correct. And it ends in FAF, which you can see here. This is the F, this is the A, and this is the F. Alright, so this is the binary representation. Now, we know that these are for the start coordinates, or the start coordinates, and these are the exit coordinates, alright? So this is what we get here, this is what we get here, so I'm just going to put that here. Now, out of these, we know that the first bit is the horizontal walls, which actually at this point I'm no longer certain whether it is in fact the horizontal rows, because I was confused about where X and Y were. So I'm just very quickly going to check which way around they were. Alright, so somewhere here, okay, so this is the maze generation algorithm. So now that we know that maze is actually, rows first and then columns, let's see where it encodes the walls, right? This is where it encodes all of the walls. Excuse me. So, this number, right, let me actually search and replace num13 with, I don't know, I. But actually, no, I can just check where this occurs. Right, it occurs right here. And, oh, sorry, I should have looked at this here. I want to see in which of these two square brackets it occurs. And it turns out it occurs in the first one, and num14 occurs in the second one, which means that this is actually the y-coordinate. Okay, so if the y-coordinate goes through all 7 iterations, then these are the horizontal walls. So the y-coordinate, let me think about this. So the y-coordinate goes through, yeah, that's right. And then the x-coordinate, so this would be the x-coordinate. Yeah, yep. This is correct. So this is actually, so I was right that these are the horizontal walls. So I actually kind of, wait, are they? Hang on. Yeah, no, that makes sense, right? The horizontal walls are the ones Yeah, I'm fairly convinced about this. So these are the horizontal walls, and I had these flipped. So because this one here says that condition, and this is the y coordinate. So this is vertically flipped if the top right LED is that, and horizontally flipped, right? Okay, so that's the first loop. Now the second loop, I'm still really confused about this, because the outer loop goes from 0 to 6. So let's see, which of these square brackets use each of the values? Well, it turns out this one is used in the first one, and this one is used in the second one. Yeah. 1 second, I have something on my finger here. I need to do it quickly. Okay. So, this is very, very confusing. Let me just quickly think about this. So here, you know what? I'm going to try something. I'm going to just set all of these to x's. Get rid of this, and now set in this line, set every pair of x's to a block followed by an x in the selection, like that. Right, and then of course that is, so these are the positions that you can be in on the maze, right? And the walls are in between those. So the first loop here, it goes, so where the y coordinate goes from 0 to 7, right? This would be 0, this would be 1, this would be 2, this would be 3, this would be 4, this would be 5, this would be 6, which is less than 7, all right? And then you can see here that when it doesn't do the flipping, it just goes 2 times that. All right, so 0 is actually line 0, and 1 is actually in line 2, and then this is in line 4, so this actually makes total sense, and 6 is in line 12, excuse me. Because, obviously in the array they would be 0 based. Not like, because the line numbers in the editor start at 1, but in the array they would start at 0. So this is completely correct. Now if it does 12 minus that, then of course 12 becomes the 0, right? So this one becomes swapped with this one up here. Alright, so this one gets swapped with this one. And similarly then of course 1 gets swapped with 5, etc. So this makes total sense, right? And then here we have 11 rather than 12. Why do we have 11? Well, because now we're not dealing with the positions where you can be, but with the positions in between, because we're looking at, bingo, we're actually looking at vertical walls. So I had it wrong the whole time. Right, so these are actually the vertical walls, and these are the horizontal walls. Okay, so these go from 1 to 6, right? And now I'm willing to bet that instead of just going 2 times, it goes 2 times plus 1. Yep, there you go, 2 times something plus 1, right? And of course 11 is the same as 12 minus 1. So it's literally, right, so the actual coordinates, like the actual indexes in the array, would be right, actually, sorry, these obviously go from 0 to 5, and then the actual indexes in the array would be this, and you can easily see that, 0 times 2 plus 1 is 1, 1 times 2 plus 1 is 3, for example, 4 times 2 plus 1 gives you 9, right, so that's what's going on here, and then in order to swap them, for example, to swap 0 with 5, you go 11 minus 2 times the number, right, so 11 minus 2 times 0 would give you 11, right? So 0 gets swapped with 5. And then 11 minus 2 times 1 gives you 9, right? 11 minus 2 is 9. So 1 and 4 get swapped. So this makes total sense. The only thing that is really worrying me is this, it's this part down here. Because here, right, if you were to swap, let's see, okay, like I said, these are y coordinates, right? So this would be a y coordinate. So if right, so if it were to swap all the even ones, it would swap 0 with 6, and that would be fine. and it would swap 1 with 5, and that would be fine, right? But then down here in this other array, right, this is all shifted. Right now we're looking at these coordinates here, and that loop only goes up to 5, right? Which you can see here, it says less than 6, so it goes up to 5. And then these here go up to 6, which you can see here, it says less than 7, right? So now if you were to swap all the even ones, then it would swap this one with this one, but not this one with this one. And this is why I'm really confused. So it suggests to me that this might actually be unsolvable. But anyway, so I've talked enough about this. What I'm going to do now is I'm going to actually just decode the bits, which I've actually already done. And I'm going to see what the pattern of horizontal walls looks like if I put them into this diagram. All right, so these are the bits, and I want each of the x's in between, because wait, we're talking about horizontal walls, which means, no, we're actually talking about the vertical walls, right? This was mislabeled, right? So these are the vertical walls, and the vertical walls are all the ones between these things. So I'm going to do this. I'm going to find me all of the x's which are preceded by a block and followed by a block. Right, there you go. Regular expression, there you go. And now I can just flip between them. And now I can literally just put the binary digits that I see down here in there. Now I'm going to group these into groups of 6 so that I can more easily see where I am. Okay, there we go. So we have the 1, then we have 0, 0, 0, 0, and then we have all zeros, and then we have 1, 1, 1, 0, 0, 1, then we have 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0. That did not go as planned. 0. Okay, which line am I in? I am in this line, right? So that should be a 0, 1, 1, 0, 0. Then we have 1, 0, 0, 1, 1, 1, and finally 0, 0, 0, 0, 1, 1. Okay, and now obviously no, actually that's not obvious. Are any of these... okay, so it never actually flips the bits, it only flips the coordinates, right? So let me make sure of that. Yeah. So yeah, it only ever checks whether it's a full block. So it never flips the bits, it only flips the the total arrangement of it. Okay, so that means that if I just change all of the 1s to vertical lines and all of the 0s to spaces, yeah, okay, maybe not literally all of them, but actually, you know what, I'm just gonna get rid of this anyway. So let's turn all of the 0s to spaces. And now let's do the same thing with the vertical lines, right? So I'm just gonna put V's here to make it easier. Replace all of those with that. There we go. And now I'm going to put these bits, these bits into there. And I'm going to group these into groups of 7, because each row of vertical walls horizontal, these are horizontal, I marked them with a V, but they are horizontal walls, I do apologize. Okay, so we want 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, and then we want 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, and finally 0. Okay, and then now I can change all of the 1s to a horizontal line, boink, and all of the 0s to spaces and all of the x's to mid dots, like this. Okay, and now I guess I can also get rid of the blocks. And now this resembles in some way the maze that we've determined, but of course some of the columns and rows may be swapped. But you can see that the first column is actually correct. Look at that. The first column is correct. And I am willing to bet that the second column is also... No, it's not correct. Right. But I was going to say that the second column is actually the same as another column, but that is also not the case. So maybe I made a mistake somewhere. Probably a mistake in walking the maze. But you can see that this column here... This column... this column very closely resembles this column, but not quite. So let me mark the places where they don't seem to match up. Let's see. We have this one here. That was... I'm going to use this to mark the places where I... where my maze is different. This is also a place where it is different. Let's see. Right, then the next column, look at this. This is all empty except for one vertical line, which means that, once again, that one is different. That is very strange that this one line would be wrong. And then here, once again, this one space is wrong, and all the rest is correct. That is extremely strange. The rest, so all of the horizontal lines were correct, except for those four. That is very bizarre. The right column should be incorrect in what you calculated because you were able to walk up and down in the right column. Well, I'm looking at the vertical walls right now, Goofy. So walking up and down is not what I'm looking at. I'm looking at left and right only. But now I'm going to look at the horizontal lines, and I think they are upside down. So if I put this line here, we can see that matches. And then this line here, we can see that is actually a horizontal flip of that. We can see here that that is a horizontal flip of it. We can see here that this is a horizontal flip of it. This is a horizontal... Yes, it is. It is a horizontal flip of that. And finally this. Yep. Okay. So I did actually walk the maze correctly. And what I would therefore expect, I'm going to scroll away the LED colors, and I'm going to say the vertical maze, actually instead of scrolling them away, let's scroll them away to the bottom. So the the horizontal walls, they were both vertically flipped and horizontally flipped. But this here never happened, which means I expect the bottom left bit 1 to be 0. I expect the bottom left bit 4 to be different. So I expect that to be a 1, right? And then the middle bit, since that was also vertically flipped, I expect that to be a 1, so I expect this to be 6. And then the other one, the vertical walls, they were absolutely correct, right? So I expect this to be false, and I expect these to be equal, which means... I know from memory that it wasn't black, but it could have been black. Black would have done the same thing, but if this is on... and this is also on. No, if this is off, and this is on, and this is also off. So I would expect that to be 4. Right, so I expect the top right to be 4. Now let's see if I'm right. For the top right LED we have blue, which is 1. Okay, so that's... so that was in fact true, and that was... Okay, so it's still not equal. So I was at least right about this bit. And then the other one, I expected to be a 6, which is yellow, and it was in fact yellow. Okay, so what I should have said here is that this would have to be different from this. So it could have been 4 or 1, right? Because either this would be set and this one false, or this would be set and this one false. So it's either 4 or 1. And it turned out it was in fact 1, which is blue. So I think that I understand the module now, and I believe that I can probably solve it using the information that I've gleaned, except that I'm still not sure about this condition here. This is still very, very strange. I want to look at the code once more to remind myself of how this is structured. I mean, it makes sense up here, but down here, this does not make sense. So what this does, right, is it sets 7 bits, starting with bit 48, right, and it will either horizontally flip this according to this LED, which never changes, so this is either true or false for the whole maze, and this one here, these are also true or false for the whole maze. But this one here depends on the y coordinate. And that, you know what? Here's what I'm going to do. I'm going to just, I have an idea. Let's see how this entire swapping happens. Okay, so if I have a string A, B, C, D, E, F, wait, we actually know how many. It should be 7. So let's go up to G. All right, so we have these 7 rows, and for each row, I check whether it is. Let's say that all of the indicators, all of the LEDs, are black. So it's all 0. Sorry, not black. Of course, this is. Yeah, okay. Let's say it is all 2 plus 4. Which is 6. So let's say the indicators, sorry, the LEDs, I keep saying indicators, let's say the LEDs are all yellow. Okay, that means that all of these conditions are false, except for the one at the bottom, which applies to the odd rows, which in this case would be this one, and this one. Okay, so now I'm going to go through this in order. So right now, my num15 variable is 0, so I'm pointing at this row here. All right? And so this boolean is now false, right? Which means that I will, I don't care about this. I want to see which row I am actually putting in. So let's see. I said that this was going to be false. Okay, but this will never matter if this is false. So let's actually say that this one is true, because otherwise, that would not matter. So in order for this to be true, so let's say the LED is in fact white. Okay, if it is white, then we get false, false, true. Yes. If it is white, then we get false, false, true. Okay, in that case, so if that is true, and this is now false, right? Yeah, we said I should probably do this. So I know in which rows that is false. Okay, so now we have a false there. So this will give us true and false, so that'll be false. X or another false is still false. And so it does get swapped, right? So here it will actually end up putting row G. Wait, okay, I'm actually looking at this, and this is 6, right? So it will only go up to F. So this will actually put F here. Let me make sure of that. 12. My gosh. Oh, now I get it. Okay, this puts my mind at ease. What this does, okay, so for each, okay, alright, now, I am now relieved. Okay, so what's actually going on is that some of the rows, some of the odd index rows, may be horizontally flipped, in which case, so what I thought is that A and F get swapped, but actually no. I mean, that is the case up here, right? Up here, no, actually it is not the case here either. Okay, this only determines whether it is horizontally flipped. Yeah, within a row. And then this determines whether the rows are swapped, and that one doesn't do. Okay, right, that puts my mind at ease a lot. Okay. So that means, right, so if I had simply changed this, I would have realized this a long time ago. So if the y-coordinate of this row is odd, then it may be horizontally flipped. Okay. I believe that I have all of the rules now. Okay, the big moment is coming, guys, ladies and gentlemen. I'm going to run the module one more time, and I'm going to try and solve it. And the thing is, the fact that it uses a proper maze generation algorithm, by proper, sorry, I don't mean, proper as in not improper, I mean a maze generation algorithm that is well defined and that well understood. So I can take the bits that I got, I can generate the output, and then I can tell whether it is in fact a valid maze that this algorithm would generate. And if it is not, then I can I can see that I made a mistake. Alright, let's get... Oh, it is difficult to tell which of the... Alright, let me... Alright, let's start by writing down all the information. Okay, so we've got a capital O with a grave. We have... So now I don't know whether this is block 1, block 2, or block 3. You see there are 3 of them. And it's looking like block 3. But wow, that is difficult to tell. Let me see what a difference that makes. How many bits are affected by this? Okay, at most 2 bits are affected by that. That is a bit of a relief. So I'm gonna take a guess and say it is this one. Then we have the horizontal box drawing character, I believe. It's a bit long for a hyphen, so I don't think it's a hyphen. Then we have this one. Then we have an ampersand. Then we have an apostrophe. Then we have DLE. We had DLE before, didn't we? It was 10 in hexadecimal. Right, and then we have a November. You know what? I think I'm going to just write down the numbers directly. And then we have this, which is this one here. So that's alpha E, alpha echo. And then finally we have the acute accent, which is this one here. That would be echo foxtrot. Ooh. It's hard to tell whether that is the actual space or the non-breaking space. So that one could be either 20 or FF, and I wouldn't know. And then we have DC3, which is one of these. That would be 13 in hexadecimal, so let's put 13. Right, that was the last one, so let's convert these.
Emergency cleared. All personnel, please return to your stations.
Okay, I'm looking at the wrong table. We're looking for the capital O, so this one here, but in capital. Capital, there we go. That would be echo 3. Echo 3. This one, my guess is that this is Bravo 2, but it could be Bravo 0 or Bravo 1, and we'll find out. This is the horizontal box drawing character, that would be Charlie 4. This is a corner piece, that is Charlie 0. This one obviously is an ASCII character, and so is this one. So, I'm just going to take a guess and say this is 20, and if... Oh, wait, I can actually determine this, because... No, I was going to say I can determine this because this is part of the exit coordinates, but it's not. The exit coordinates are entirely in the last byte, and the start coordinates are entirely in the first byte. So that's a bit inconvenient. So I'm going to take a copy of this, but then change this to 20. And now let's change all of the spaces to nothing. Oops, I meant all of the spaces in this line. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, let's turn these into that, from hexadecimal to binary, thank you. So that would be these, and then we have, I should probably make sure that we have the right number of digits. That is 48 digits, yes, that is correct. This will be fewer digits, so I will need to pad this with zeros, and indeed we want a 1 followed by a 0. This this is very similar to what we had last time. Okay, so the starting coordinates are consist of those 6 bits, and then the exit coordinates consist of these. So I'm just going to say exit and start, and I don't care about those just yet. Now let's generate the maze. Whew. What is the most effective way of turning these? So it's the vertical walls first, right? So I want to, yeah, here's what I'm gonna do. I'm going to turn, yeah, okay, so this is just the vertical walls, right? So I'm gonna turn the ones into vertical box run characters. I'm gonna turn the zeros into these block 1 characters, and then I'm going to put spaces after everything. And now I know that there are 7 walls in each row. So these are the rows, like that. Right. And now I'm going to take the horizontal. Let's take the horizontal ones. Now this time we have 6 per row, and 7 rows of them. And all of the ones I'm now going to turn into horizontal lines. All of the zeros I'm going to turn into, let's say, block 2, just so that I can distinguish them. And now I'm going to interweave them. So, oh yeah, sorry, I want to space them out as well. So let's do the same thing that I did here, like that, to space them out. Right, and then I'm going to put a space in front, and then I'm going to move that here, move that here, move that here, that here, that here. Okay, why did I run out of them? Right, because I'm dumb. I should have started at the top. That goes here, and that goes on the bottom. Okay, so obviously this is not a valid maze, so now I need to use the LED colors to determine which of these rows I need to swap and which ones are flipped. And as I say this, it occurs to me that maybe I should have done the flipping on the zeros and ones, whatever. So the LEDs, let's take a look at the LEDs. The LEDs are, so we don't care about the top left and the bottom right one because those only apply to the start and end position. So we care about the one for the vertical walls is green, and the one for the horizontal walls is cyan. Now green in our color scheme here is of course 2, which is 0, 1, 0, and cyan is 3, which is 0, 1, 1. Okay, so what do these mean? Well, okay, so for the vertical walls, which are, I want to close this tab, and I think I want to close this tab. No, I don't want to close it, but I want to, I do want to close the tab, but I don't want to lose the information. Okay, this is vertically flipped if bit 2 is set. Unfortunately, both of them have bit 2 set, which means that everything is vertically flipped. So let's actually, let's do the horizontal flipping first because it depends on whether the y-coordinate is odd. So I'm going to do that first. So which of them are horizontally flipped? Let's see. Is the LED bit 4 set? No, for neither of them. Is the LED bit 1 set? Well, for the vertical walls, no. So this is always false, therefore this is always false. And this is also false. Therefore, it is just always false. Therefore, the vertical walls are never horizontally flipped. Okay, whereas the horizontal walls, they may very well be flipped because of this bit here. Right, so every odd positioned row of horizontal walls, let's see, is flipped if, oof, this is so difficult. Okay, so this is our expression, right? So this is the entire parentheses. Okay, so the bottom left LED bit 4 is 0. The bit 1 is 1, and 1 and something is just the something. And so if this is not equal to 0, then that is the same as true. Okay, so that means all of the odd valued Okay, horizontal wall. So let's see. This is a horizontal wall line, but that one has an even because we start counting at 0. So we need to horizontally flip this one. So I'm going to move that here. And then we need to horizontally flip this one. So that goes here. And that goes here. Like that. And that is exactly wrong because I said only the odd numbered ones. So this one here, I can flip that just by moving this to here. That's basically the same as flipping. And then this one here we need to flip. So that goes here. And those two swap and they're already in the right place. So I think that the horizontal walls are in the right places now. No, wait, we still need to check whether it's vertically flipped. It is vertically flipped if bit2 is set, which indeed it is. But then again, it is set for both of them, so I'm actually going to do the vertical flip at the very end. Okay, so wait a second, but that would mean that this should already form a valid maze, because we've done all of them, but it doesn't look like a valid maze. Let me just quickly remove all of these block characters. Yeah, that is definitely not a valid maze, because right here, up here, we have a cell. Oh, wait a second, I think I might have messed up by moving things. Space, right, I didn't... Ah, there we go. So that is definitely an invalid maze, right, because you can see this section here that consists of that horizontal corridor, this part, and this part, is cut off from the rest of the maze. And by the way, so is this part here. Oh, wait, is it? No, it isn't, because... wait, if this is a horizontal, if this is a vertical, wait, whoa. Ah, okay, wait. So did I do this even? Did I do this right even? Let's see. So the vertical walls. Yeah, I think. Ah, okay. So when I did the vertical walls, did I split that into groups of 6 or the groups of 7? 1, 2, 3, 4, 5, 6. It seems. Yeah. So these are just out of kilter, right? Let me just undo this. So right, okay, I did this wrong. So the vertical walls should be 6 per line, and the horizontal walls should be yeah, okay. So this is just completely wrong. So I'm just gonna redo this from scratch. Okay. Let's do this. Okay. So what I did wrong here is I grouped this wrong and I aligned this wrong. So we start with the vertical walls, and the vertical walls, there are 6 in each row, and there are 7 rows of them. So I'm gonna do 6 bits at a time and change all of the 1s to a vertical wall and all of the 0s to a little sort of shaded block, and then put a space after everything, and that is our first iteration. Now for the vertical walls, because of this, let's see, it is vertically flipped, but all of this is 0. So it is never horizontally flipped. So these should be the vertical walls, full stop. And now the horizontal walls, they come in, yeah, 1, 2, 3, 4, 5, 6, 7, rows of 7. Okay, now this time I'm going to do the flipping first. So I believe that all of the odd numbered horizontal walls, so that would be this one, and this one, are horizontally flipped. I noticed that the bottom row is entirely 0. That is unusual, but not impossible. Okay, so we want to flip this one here, which would be 0, 1, 1, 1, 0, 1, 1. So let's try that. And then 1, 1, 0, 0, 1, 0, 0. So let's try that. Okay, and now all the 1s are a horizontal line. Yeah, let's do that. And all the 0s should be something like this. And then we space it out like that and put that here. And now we put a space in front here, and then we put that here, And I did it wrong again, didn't I? That should go here, 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 and here. Does that look like a valid maze? Right, let's remove all these block characters. Like that. Yeah, that actually looks like a valid maze. Look at this, everything is connected. There are no loops. This is absolutely fine. This is a totally correct maze, except of course that it is upside down, but it is horizontally fine. So what I'm going to do is I'm just very quickly going to flip it vertically, and in order to make sure that I don't get confused, I'm just going to number the rows first. So this is 11, this is 12, and this is 13, and then 13 obviously goes on the top. 12, 11, 10, 9, 8, 7, 6, I put the 9 there. See, the fact that I put the numbers there made it very easy for me to fix that mistake there, so that was pretty cool. Alright, so I believe that this is now the correct maze. Now to make this maze a little easier to read, first of all I'm going to change all of these, because I don't need the distinction between the two different kinds of blocks anymore. So I'm going to change these. And now, all of the blocks that have a space between them, I'm going to change that to a mid dot, like this, in the selection, 1790. And then, I also want to change all of the spaces in the even numbered, all of the spaces in the even numbered rows, I want to change them to mid dots. So let's get rid of these numbers and change all of the spaces. Right, let's get rid of the trailing spaces, change spaces to this in that selection. And then here, and then here, and then here, and finally here. Okay, now I should be able to remove the blocks, and that should now look like a... change the blocks to spaces, and that should look like a totally fine maze now, and it doesn't. I've made a mistake. Okay, this shouldn't be a space. I mean, this shouldn't have a dot in it. Yeah. Okay, let me think about this. Like, which ones of these should actually have dots in them? Right, well, definitely not this one. Alright, let's do all these. Let's remove all of the ones that I'm sure shouldn't have dots in them. Okay, now let's try that. I'm making this harder for myself than necessary. Okay, finally, that looks like a perfectly fine maze. Okay, I believe that this is the maze that we are in. And now I need to decode the start and end position. Okay, so the LED for the start position, which is the top left, is cyan, which is 0, 1, 1. And the one for the end position is white, which is 1, 1, 1. Okay, cyan is 3 and white is 7. So, let's see, if bit 1 is set, then X and Y are well, actually, let's do the negation. Should I do the negation first? Because in the code, it does the swapping last. So yeah, I should do the swapping first. Alright, let's close this empty tab. So if bit 1 is set, then X and Y are swapped, which in both cases they are. Right, so X and Y will be swapped, which means that, so normally X is first, but now Y would be first. Okay, and then, right, okay, so let's put them in. So this would be 7, 0, and this would be 2, 3, right? And then X is negated if the middle bit is set, which is the case in both cases. So that becomes a 7, and that becomes a 4. And then Y is negated if, Y is negated if bit 4 is set, which is only the case here, so that is actually a 5. 2, 4, 4 plus 1 is 5, yes. So I believe that these are the coordinates that we need to care about. So this should be um, once again, we shouldn't be getting a 7, should we? Yeah, the starting position can never be a 7, so I must have messed this up. I probably swapped the x and y again. Let me just quickly look at the source code to see what order it puts them in. So it definitely puts the... right, let's see. Okay, so here it uses start 0 to index into the first index of maze, which indicates that start 0 is in fact the y coordinate. But here it does the 1 minus thing, which means that it encodes the x coordinate first. Right. So it encodes the x coordinate first, then it decides whether to mangle the x coordinate. Here it decides whether to mangle the y coordinate, and then here it decides whether to swap them. So I should be doing this in the opposite order, right? So if, let's see, if the lowest bit is set, which is bit 1, yeah, if that is set, then they are swapped. Let me do this, x, y. So if this is set, then they are swapped, which means that instead of this being 7 and 0, it would now be 0 and 7. And this, instead of being 2, 3, would then be 3, 2. Right? That should be the x and y value. And then we go to this, where it says if the middle bit is set, then we negate the... we negate the... Okay, I see. So here's what I'm going to do instead. Instead of writing down x and y, what I'm going to do is I'm going to do the same bit manipulation that the code does. So the first manipulation, or rather the last manipulation, but I'm doing it in reverse, is to swap the two values like this, right? And then what it did before that is to decide whether the second value, whether that's x or y, at this point it would be y, so that depends on the middle bit, and the middle bit is always set. So yes, so this is definitely a 0. Bingo. So I did do it wrong. I did get it wrong. And then here, this is negated. Right. Okay, so that means our start position is in fact alpha 1. So we start right here at the top. And our goal is, let's see, that is 4, which would be echo. And then 5, so 6. Echo 6, right? So A, B, C, D, E. 1, 2, 3, 4, 5, 6. This is my goal. And now I'm going to find a path. Aha, and I found a path. So I should be able to press... Right, actually I should be able to tell from the module that I am in the top left corner, which I totally didn't actually pay any attention to, but I'm very glad to see that that is confirmed. So I should now be able to go down, right, right, down, right, excuse me, up, right, down, left, down, right. And I claim that that will solve the module. Let's see. Down, right, up, right, down, right, down, left, down, right. Submit. And, drum roll, the answer is... correct! Oh my gosh, yes! I've done it! First try! No strike! Yes! Ladies and gentlemen, we've done it! Whew! Okay, there has been no comment from the chat, but you know what? I'm just quickly going to do another one. Because, woohoo! I can do this now. I know how to do this module. Alright, let's do this again, ladies and gentlemen. I'm just going to do the whole thing. Alright, let's start with this. First character is delta 0. Second character is... you know what? Can I... I'll write them down first. We have this, then we have mu, then we have H, BS, O. I'm pretty sure that's a capital O and not a 0. Then we have this, BS, and then E. And then we have Sedalia. then we have an @ sign, and then we have this. And that should be it. Okay, let's do them in backwards order, I guess. Charlie 5, @ sign is... oh, of course, that's ASCII. Oh my gosh, I'm not paying enough attention here. Now the cedilia is here. So that is Foxtrot 7. Let's find that echo. That would be this one here, 8 alpha. BS is of course in here. That would be 08. So that's 08, that's 08. And then we go back to this and we find Charlie 8 here. Oscar is of course 4F. Hotel is that. The mu is Echo 6. And then we have this one here. That is Bravo Bravo. All right. Let's divide this up. Remove the spaces. Turn this into binary. Here we go. And this. Okay, so our starting position is this.
Emergency cleared. All personnel.
And our exit position is this. So I can already tell that this can't be inverted because that would make it a 7, which is impossible. Okay, and then we have, let's see, we have the vertical walls first, and the vertical walls, this time I'm going to get it right. The vertical walls come in 7 rows of 6. So, let's do that. 1, 2, 3, 4, 5, 6. Boink, 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 boink. Alright, so all the 1s become vertical walls. Boink. All the 0s, I think I'm just gonna use dots this time for the things, and then everything should be spaced out like this. Alright, that's our vertical walls. Now let's take a look at the... Yeah, let's do the horizontal walls first. Now this time, 1, 2, 3, 4, 5, 6, 7. Horizontal walls come in rows of 7, 6 rows of 7. So now the 1s become a horizontal line, and the 0s, I'm just going to turn those into mid dots. There we go. Space everything out and put that here. And now I need to figure out which ones of these are swapped, or rather flipped. So our for the vertical walls, the LED we care about is green, which is 0, 1, 0. Right, that's a 2. And it is vertically flipped if bit 2 is set and everything else. So if that is false, then that is false, and that is false. So nothing is horizontally flipped, so it's just vertically flipped. So let's just vertically flip it, right? 7, 6, 5, 4, 3, 2, 1. Done. Okay, so we're done with the vertical walls. Now for the horizontal walls, the LED is cyan. Cyan is 0, 1, 1, which means that it is in fact vertically flipped as well. So I need to flip that. There we go. But now we have that extra complication, which is that... right, let me simplify this. So it is horizontally flipped if 0 is not equal to 1 and means just that. So if it's horizontally flipped if y is odd. Okay, so that means this is horizontally flipped. So we can... Once again, I should have done this with the bit representation, but actually I just need to swap those two. Okay, and then in here I need to put this one here and this one here. And finally here, I need to, you know, this time I'm gonna do it like this. Like put that here, and then we have 2 of these, and then we have 2 of these, and that. Okay, so none of these were vertically flipped. No, both of them were vertically flipped, but I already did the flipping, didn't I? Alright, let's put all of this in here. Oh, no, I first need to, right, I just need to put a space here. Oof, okay. Getting really nervous here. Let's put all of this here, that here, that here, that here, that here, that here. And does that look like a valid maze? Right. For a moment there I thought it didn't, because I thought that this area here looks like a loop. But this here and this here, these are not positions that you can visit. This one is, right? So you can go up here, you can go right. So none of this is actually, ooh, shit, this is actually a loop. So there is a loop. And also there is a bit up here that is cut off. Okay, so I must have made a mistake. Let's see. Hello, Livio. Welcome to the stream. By the way, the title is still adding souvenir support. Oh, thank you. Thank you. I totally forgot about the title. Ah, god damn it. Decoding a challenge module. ASCII Maze. Thank you very much, Livio. Why do people not tell me that? I've been streaming for 2 hours, 20 minutes and nobody told me this. Okay, so clearly I made a mistake somewhere. So I'm gonna try this again. In fact, wait a second. If I were to horizontally flip this, then that would make the top row more likely, yeah, that looks more valid, doesn't it? This one here looks fine. This looks fine. Aha, so if that is flipped, and I think the bottom one has the same thing. So if I just put these here and put that here, yeah, and that looks much more valid now. So I think that some of the, aha, so this should probably also be flipped. If this line was flipped, then that would fix these. So I think that what I did is I just flipped the wrong lines here. So let me just quickly check which ones I flipped. I flipped this one, and the last one. Yeah, that should have been correct. So I guess, all right, let me undo all of that flipping, and let's just interweave them now without any of the flipping and see how close to valid that looks. That is obviously still not valid. Okay, so I do need to flip some of them, but it seems to me that I've flipped the wrong ones. I clearly need to flip the top one, right? If in order for that to be correct, assuming, of course, that the vertical walls are not flipped. Phew. Okay, so I need to make sure. I need to figure out where I made a mistake. So let me just quickly restore all of this. Okay, so right, so this is the raw data, right? This is 0, 0, 1, 0, 1, 1, 1, 0. Yeah, so this is before all the flipping. And this is 1, 1, 0, 0. Yep, that looks like that. Okay, so this is the raw data. Now the top right LED, cares about the vertical walls, which is these. Yeah, and the top right LED was green, which is 0, 1, 0. Okay, so green, let's see. So it is vertically flipped. Yes, it is vertically flipped. Is it horizontally flipped? Well, this bit is 0. This bit is 0. 0 and anything is 0. And 0 is not equal to 0 is false. So no. So it is never horizontally flipped. So this should be correct, right? And then this one here was 0, 1, 1. Right, it was cyan, wasn't it? Bottom left, is bottom left the right one? Yes. So 0, 1, 1 should be right. And then bit 4 is, of course, a 0. Bit 1 is a 1. 1 and anything is the anything, so it's that. And that means if y is odd. Let me just quickly look at this. So in this piece, right, it's this condition here that asks whether it's odd. I think I did this right. All right, let me look at this expression here. I'm going to check this out. So this determines whether it's horizontally flipped, right? And 1 here is the fourth bit, whether the fourth bit is equal to 0, right? And that is a yes. That is a true. I'm trying really hard here to get this right. So this is in fact... Oh, no. Oh, god damn it. 1. No, that is that one. Alright, so that is true. Okay, so number 2, which would be this one here, checks whether the bottom bit is 1. That is a true. Right, that is equal to 1. Yeah, that looks fine. And then the third thing is whether it's an odd row, right? Now, true and something gives you the something, and then true x or something gives you the not of that, and then we have 2 nots, so odd. It should be horizontally flipped exactly when it's... That is so surprising. Okay, let's... Oh, I think I get it. Okay, I figured it out. How many of you have figured it out? Okay, so here's what happened. This oddness criteria applies to the original index of the row. And remember, I numbered these, right? And you will notice that the first one is even and the bottom one is odd. But what I did is I did the vertical flipping. You know, I flipped these like this, and then I treated them with, you know, as if they were numbered from 0. And this is why it looked like everything was flipped, because I flipped exactly the wrong ones. So, this is the vertical flipping that it should have. And I'm just quickly going to apply the same vertical flipping here. I should probably not, I should probably do this. 0, 1, 2, 3, 4, 5, 6. There we go, put the 6 there. 6, 5, 4, 3, 2, 1, and 0. Right, and now, instead of doing the odd numbered ones, which would be this one, and this one, I need to do the even numbered ones because I did do the flipping. Okay, so that means that these go here, this goes, that goes here, and then here, we can just move that to here. And that should be correct now. Famous last words. This should be correct now. Everything should be working fine. Nothing should blow up, and nobody should die. Ideally. And it looks like a valid maze. Ladies and gentlemen, we've done it. Okay, so that is a lesson learned, right? You do the horizontal flipping first before you do the vertical flipping, because the vertical flipping, at least with the horizontal walls, flips the parity of the indexes of the rows. Okay, now I need to look at the x and y coordinates of the starting positions and the exit. Whoops, that's a 0. So here we have 0, 0, 0, 1, 0, 1. Now the top left LED is green. Yeah, so green means 0, 1, 0. That's the LED. So let's see, only bit 2 is set, which means that the first value is negated. So that is actually a 1. Which means that we're looking at Bravo 5 here. Okay, the second LED, the last LED is black, which means that no changes are necessary. So this is 4 plus 1 is 5, so we're looking at alpha 6. So I'm in Bravo 5, 1, 2, 3, 4, 5, and I want to go to alpha 6, which is here, which means I can go up, left, down, down. That is my claim. Up, left, down. Okay, I got something wrong. Right, let's take a look at the log file to see what the actual starting and end position is. And the starting position is goal 4, but I did get the exit location correct. Okay, let's quickly press the reset button. And in fact, I can tell from the arrow that I should be in goal something. So let's figure out why this was wrong. The starting position... do I still have the original raw data? No, I don't. Well, okay, let's just look at the very first byte. The first byte was this one, which is delta 0. Okay, delta 0. What's delta 0? A base converter. Delta 0 from hexadecimal to binary is that. Close that. And we're looking at the first 3 and the next 3. Okay, so these values are correct. But now let's take a look at the first LED, which is green, which is 0, 1. Green is 2. Yeah, so that's 0, 1, 0. Right? So these 0, 1, 0. So bit 2 is set, which means that X is negated and everything else is fine. Okay. So that actually means that Y is negated. Because Y is the one that is being negated. So I guess I got these wrong. Let me just quickly, because now that I have a better understanding of which indexes are which, let's see. This here. Right, so if the 4-bit is set, we negate the value that comes up first. Right. And this is the second, right, okay. Aha. So I should probably say first value negated, second value negated, and then if this is set, then values are yx, else xy. This is how I'm going to write this in the manual. Okay, so now I need to negate the second value, which gives me 0, 1, 1, which is 3, so that becomes a 4. And then this here is 4 plus 2, which is 6. 6 plus 1 is golf. I get golf 4, and indeed golf 4 is what it said. Okay, so now I am not here anymore. I'm in golf 6. 1, 2, 3, 4, 5, 6. Right, so from here, I want to go... Let's see, there's a big wall here, and this is where, right here, this is where I go through, yeah, so I want to go, let's see, I want to go up, left, up, right, and that will put me here. Up, left, up. It says golf 4, not golf 6. Why did I think I was here? I am, of course, here, which means I can just go up, which means I'm now here, and now I can go 2 to the left. I am now here, and then we have down, left, 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 down, left, left, and then up, left, down, submit. Okay, here we go. It is correct. Right, so this time I got 2 strikes because I made 2 dumb mistakes. Okay, there is definitely a lot of work involved in this module. And there are 2 little things like, in decoding these characters, it is difficult to distinguish these three characters, and for some people it might be difficult to distinguish the horizontal box drawing character from the hyphen. Oh yeah, and also the non-breaking space. Oh wait, actually we can take a look at the code, and there is a chance that the non-breaking space isn't... There you go, it actually says NBSP, so you can distinguish that from a space. So the actual space is an actual space, right? So if there's nothing there, just space, then it's the space, which is 2, 0. Okay. Right, let me take a quick look through the rest of these. Yeah, it does have these block characters there, literally. Okay, so I believe that we've decoded the module. And the module deals with the code page 850, not ASCII. And with that, I think we're ready to write a manual. Okay, so for the manual I definitely need a table of these values, right? So, and of course also these ASCII. Let's see if I can find an ASCII table that I can actually copy and paste. Bingo. By which I may... Oh, wait, I was going to say I wanted to copy and paste the actual characters, but why don't I just copy them straight from the source code, because it's right here. I should have thought of that. Okay, So these are the actual characters as they are shown on the module. What is this? This is very interesting. What is that? I'm kind of intrigued by that. Oh, it's the soft hyphen. Ha! I'm not quite sure what is displaying here. Okay, AED. Soft hyphen, right, okay. So the first one is a soft hyphen. That one is also a soft hyphen. And then it has this character, identical to. Okay, very strange. Right. Okay, so I'm going to do this. I'm going to put a comma here, and then I'm going to do this like that. Okay, so these are all. Oh, interesting that it didn't remove these. Oh, because there is a space after it. Okay, fine. There. Okay. So I want. Oh yeah, that should be a space, obviously. Oh, and some of these have backslashes. I should probably check for those. So, those are the only ones. That's good. Okay, now I want to turn this into an HTML table. So first of all, let's just take any random manual and save it as ASCII Maze.html. Okay, it does not have rule seed, at least not yet. Not until I get my hands on it. I imagine that one way to implement rule seed support is to use a different code page, right? This one uses code page 850, but as we've seen before, there is this other code page 437, and I assure you there are several others. These are just the two most common back in the DOS era. So, you know, this one here will use some character, like including Greek letters, which this one here doesn't. Right, anyway, back to this. Okay, so we don't need a script tag. Alright, on the subject of ASCII mazes, I guess. What would be a good flavor text? Why is it called ASCII? Because it doesn't use ASCII. Alright, let's do this. Okay, so first of all, on the bottom of the module, the screen on the bottom of the module can be scrolled through to obtain how many characters are there. Let's see, we have 42 times 2 plus 6 twice divided by 8 is 12, right? To obtain the screen on the bottom of the module can be scrolled through to obtain 12 characters, which are delimited by what was the it was FFDF. Is that the right one? No. FDFF, I think is what it was. No? Okay, replacement character. There we go, FFFD, that's what it was. FFFD. And that one looks right. So, which are delimited by use the following table to convert these characters to binary. The table shows their values in hexadecimal, or at least, you know, actually, why don't I actually just show it in binary? That's actually a good idea. All right, so I'm quickly going to write some code that does this, which reminds me I could probably use with this being a valid array declaration. So I'm gonna undo to get all of these. There we go. Okay. Let's run Visual Studio and let's run temp. Come on, there we go. So our array is going to be this. And now I'm going to say, so we want, so it's 255, 256, which is 16 times 16, so we probably want 16 rows of 16 characters. Right, so we're going to say for each row from 0 to 16, we are going to output something that has a table row tag at the start and end, right? And then we're going to put the row, the table row in there, right? And table row is going to be a string builder. And now for each column from 0 to 16, I'm going to add, or rather append, something that has td/td in it. Now, the first thing that it has, I'm going to put that in a div. That would be the character, and the character is, of course, array of 16 times row plus column /div, and then I'm going to say code /div. Now, the code is, of course, 16 times row plus column, but in binary. So convert to string that in binary, and then I need to pad that left to a total width of 8 with the character 0. All right. Now I'm going to say append line so that it's all... No, because this is a single row. Right. So let's just run this, see what comes out. Now I don't trust this to copy and paste all of these characters correctly, so I'm actually going to create yet another string builder and just say sb.append, and this time append line, and then I'm going to set this into the clipboard. Let's do that. And then once I've done that, I can paste it right here into the table. Alright, so this is my little table. Little. Okay, let's do this. And now in our table, which I'm going to call codes, I guess, in our codes table, we have the actual, so the characters are going to get a font size of, let's say, 18 pt, because they can be large. And then the codes are going to be, let's say, 10 pt or something. All right, let's see what that looks like. Go here, ASCII Maze. And that is, of course, way too wide. Okay, so so first of all, I'm going to remove all of the padding. Okay, now I'm going to reduce the font size for the codes even further. Yeah, this is getting dangerously small, isn't it? But in order to fit it onto the page, I need to make it even smaller. So this would fit hypothetically, but now some of them are too big. Okay, so that would fit. Let's also give this a text align center, so it looks better. And I guess this can be slightly bigger, but not that big. Let's see. Let me see if this is off the margin. Yep, it is. I saw that. You can see that the page content margin on the right cuts into the table. So I'm going to make this slightly smaller. Okay, that should fit. And I can give the table itself a width of 100%, so we get a bit of a semblance of padding. In fact, there is enough... Yeah, there is enough space above and below the table to have vertical padding. So I'm going to say this. All right. So that's the first page done. The screen on the bottom of the module can be scrolled through to obtain 12 characters which are delimited by thong. Use the following table to convert the characters to binary. Now the following table, I'm going to put a little asterisk there and give that a footnote. In fact, let's superscript the asterisk. Right, and then here I'm going to say font style italic, superscript asterisk. This code, this table. What do you say? This table contains encodes right, this character encoding is, what was it? Ah, there, code page 850 is code page 850, or yeah, let's call it DOS code page 850. There you go, /p. All right, right. So far, so good. Okay. Okay, this is a table of character encoding. I'm being too much of a perfectionist here. I'll just leave it like this. Okay, page 1 of 2 is done. Now on the second page, get rid of all of this. We're going to explain exactly what to do. So, okay, H3, I guess, disarming the module. Okay. So first of all, let's decode the LEDs, right? Yeah, that's right. Obtain a 3-digit binary code for each LED in reading order. And then I'm going to create a tiny little table here. And this tiny little table, I don't need this code anymore. Well, I think I'm going to keep that code though. Let's see. So first of all, I want each of the 8 colors, let's see, to turn into a table cell. And the color name is going to be, let's see, black, blue, green, cyan, red, magenta, yellow, white, index. Right, and then we put that in one line. Thank you. So that's our first table row, /tr, and then the second table row is of course the convert to string of the index into binary and then pad left to 3 digits. Let's do that. And then see what that looks like. Yeah, okay. So actually, I should have realized this. I can just write out the colors. That's blue, green, cyan, red, magenta, yellow, and white. There we go. Let's let's actually just. Well, I don't know if I need a class for this, but I'm going to do this. Text align center, and I'm going to do that for all TDs. There you go. Obtain a 3-digit binary code for each LED in reading order. Right. Okay. Let's see. So the next thing I think I want the user to do is to obtain the vertical and the horizontal. So the vertical walls first. Okay, so oops, /li. So take the 7th to 48th bit. Yeah. Okay, so let's see. I want to give this code a name. The screen and character. Use the following table to convert these characters to binary. Call this the main code. Right. Take the 7th to 48th bit from the main code. Group these into, okay, these are the vertical walls, so we need 6 rows of 7 walls. Yes. Group these into 6 rows of 7 bits. Should this be plural? I think this should be plural. Group these into 6 rows of 7 bits. Right. Now, what do we need to do? So first of all, we need to do the horizontal flipping first, before the vertical flipping. Right, so let's see. I want to write this down in... So here's the thing, right? There are 3... Well, actually 7, right? There are 7 possible combinations that the LEDs can be, but the middle one is the one that determines the vertical flip. So we actually only care about the first and the last, and there are 4 possible combinations of those. And if they are both 0, then there is no flipping. Right, if this one... Well, in fact, if this one is 0, then all of this is 0, which means LED bit 4. Yeah, so horizontally flipped. So all of them are horizontally flipped at this point. Right, now let's take this original formula again. I just noticed that there is a close parenthesis missing, and none of you noticed that. Right, let's take this formula again. Right, don't need that, don't need that. Now if bit 1 is set, then this is of course y is odd, which means that if bit 4 is 0, right, then this would swap the odd rows and this would flip the even rows. Okay. I think this is correct, except of course that the user is going to is going to number the rows from 1 onwards, which means that odd and even are going to be swapped. Right, so now let me just very quickly make sure that I got I'm just really paranoid that I get this wrong. So if bit 1 is 1, then this says y odd. So if this is 0, then y odd, yes. And if this is 1, then y even. Okay, so this is going to be even rows according to the user's counting. So take this and group these into 6 rows of 7 bits. Number the rows 1 to 6. Alright. It just occurred to me that because the vertical flipping is determined by the middle bit, I can actually just take the middle bit out and put it at the end like this, right? And then instead of calling it a 3-digit binary code, yeah, okay, I see. Okay, here's what I'm going to do. I'm going to come back to this code here. I'm going to convert this, right? So let's turn this into a statement so I can do some manipulation with this. So this is the binary, I guess, like that. And then instead of just putting the binary in there, I'm going to say okay, so for each color, it's going to be one of those 4 possibilities, right? So I'm just going to, so for the horizontal flipping, I only care about the first character from that string, which is the 4-bit, and the, yeah, actually, you know what, I'm just going to write, okay, like, I'm going to write it like this. So if the 4-bit is set, then if the 1-bit is set, then odd rows, right? So I'm just going to say odd, else, this one here, all, else, if binary, so now we're here, so even, and now we are here, so none. Okay. Now obviously these are characters rather than bits, so I'm gonna say if that is equal to 1, if that is equal to 1, and if that is equal to 1. Okay, so now if I run this, so I'm just gonna leave the 3-digit code there for now. But there we go. So these are the horizontal. So this determines which rows need horizontal flipping. All right. So take the 7th to 48th bits from the main code. Group these into 6 rows of 7. Number the rows 1 to 6. Use the color of the top right LED in the following table to determine which rows need to be horizontally flipped. All right. So I'm gonna comment this out, but I'm gonna keep that information around. Okay. Use the color of the top left LED in the following table to determine which rows need to be horizontally flipped. Oh, okay. And flip them. And flip them. Right. So here's the thing, right? I can use the exact same table to also say which ones need vertical flipping, right? I'm just gonna say, so I could actually do something like this here, class corner, and then add a header here and say horizontal flipping and vertical flipping. And vertical flipping is just gonna be yes or no, right? So here I can just say return td, and then I'm gonna say if binary 1 is 1, then yes, else no. Bang. Okay. Okay, since the explanation already mentions the flipping, I'm going to remove that word just so that I don't waste too much space on the page. So use the color of the top right LED in the following table to determine which rows need to be horizontally flipped and flip them. Then use the same table to determine whether or not to vertically flip the order of the rows. There we go. So that will tell you what to do. So this is where you flip them. Okay. So now take the 49th to 90th bits from the main code. Group these into 7 rows of 6 bits. Number the rows 1 to 7. Use the same table above to determine which rows need horizontal flipping and whether to vertically reverse their order. I should probably use the word reverse instead of flip here. In fact, I don't even need vertically there, so whether or not to reverse the order of the rows. Use the same table above to determine which rows need horizontal flipping and whether to reverse their order. Okay. Interweave the lines in such a way that a 7x7 maze is constructed. Take note, note that the horizontal walls, okay, that the first horizontal wall of each row is horizontally in between. I should probably, because here I've only told people to take the bits and to flip them. I didn't tell them to turn those into walls. Right, okay. the result specifies the horizontal walls. Wait, it was vertical walls first. The vertical walls in a 7x7 maze. Right, uses into, right, again, the result specifies the horizontal walls of the same maze. Interweave the lines in such a way that the 7x7 maze is reconstructed. Note that the first horizontal wall of each row is horizontally in between the first and second vertical walls above and below it. Similarly, the first vertical wall of each column is between the first two horizontal wall columns. Right, let's phrase it like that. Let's see. All right, we still have a bit of space left on the page. Now we need to use the first 6 bits to get the starting position. All right. So first of all, let's do this. Okay. Let's see. How do I phrase it? I want to phrase this in such a way that I can use the same instructions for the start and the exit. But anyway, I think I'll just describe the start first. Right. Use the first 6 bits use the first 6 bits to obtain your starting position in the maze. Call the first 3 bits alpha and the next 3 bits bravo. Okay. Yeah, I think I'm just gonna, I'm gonna later say that this is the start position. Call the first 3 bits of the main code alpha and the next 3 bits bravo. Alright, now use the color of the top left LED in the following table to determine to obtain some steps to perform on these values. Right. Oh, sorry, I need the table in here. Okay. So once again, we're gonna use this same code to go through all 8 possible LED colors, right? And for each, you know what? I think I'm just going to call these like ABC, I guess, equals binary 0 equals 1, binary 1 equals 1, and binary 2 equals 1. Right, and then I can just call them ABC. I think that's a bit easier. Okay, so what were the instructions? The instructions are, if bit 4 is set, which is A, right? Wait. Ooh. Right, I'm gonna do this differently. Right, here's how I'm gonna do this. So, sometimes the x coordinate is A and the y coordinate is B. Right, and if the bottom bit is set, then they are swapped, like this. Right, now if the next higher bit is set, then the second value is negated, right, which is sometimes A and sometimes B. So I'm just going to put a tilde in front, like this, right, and then in the remaining cases, we put a tilde here. Right, and then these are literally the table cells that I'm going to use, and then I'm going to explain what the values and the tilde means. How about that? Alright, so that's a table row. And then of course the first table row is going to be the exact same as this one here, because this is the LED colors. Right, it just occurred to me that instead of this TD corner here, I can say LED color, and then that should, bingo, that should be clear. So call the first 3 bits of the main code A and the next 3 bits B. Use the color of the top left LED in the following table to obtain some steps to perform on these values. Right, let's do this differently. Use the color in the following table to obtain your starting position in the maze. The first value is the x coordinate. The second, right, the x coordinate or column is the zero-based x coordinate. The second is the zero-based y coordinate row. Okay. A tilde means that the 3 bits must be negated. Alright. Well, means to negate the 3 bits. That saves me 1 line. Haha. Right, call the first 3 bits of the main code A and the next 3 bits B. Right, use the color of the top left LED in the following table to obtain your starting position in the maze. The first value is the zero-based x coordinate. You see, now I'm a bit I suspect that this might be confusing because when it says the first value, this suggests that, you know, I'm talking about the first value obtained, which would be A. But yeah, but actually I'm not calling this a value, so actually I'm fine. The first value is the zero-based x coordinate. The second is the zero-based y coordinate. A tilde means to negate the 3 bits. I think I'm happy with that, actually. So it just occurred to me, I think I want to check, aha, see the upper table here cuts into the margin, so I'm going to quickly change the padding on all TDs a little bit. So I want, what is the padding at the moment? Let's find out what it is. It is this. So I'm gonna change just the horizontal padding. So this is vertical padding. Oh, and it's measured in EM instead of centimeters. Alright, so 0.6, let's change that to 0.4, I think. Alright, that's good enough. Right, but we can also make the tables full width, I think. Right, not just this table. Alright, that looks nicer, I think. So call the first 3 bits of the main code A and the next 3 bits B. Use the color of the top left LED in the following table to obtain your starting position in the maze. The first value is the zero-based x coordinate. The second is the zero-based y coordinate. A tilde means to negate the 3 bits. Yes, okay. Use the last 6 bits of the main code in the same way to obtain your goal position in the maze. There we go. And then navigate the maze using the arrow buttons on the module. When you are on the goal position, press the green, what can I reasonably call this? Can I call this a target? Is that what that shape is called? Call the green button with a target symbol to submit. The module is disarmed if the goal position is correct. if the position is correct. Otherwise, a strike is incurred. The red button with an exclamation mark can be used to reset your position in the maze to the starting position. Okay, I think that's it. Alright, we can remove this bit now. That's down there at the bottom. There we go. And that is quite dense text. You know what, I think I'm going to just space this out just very slightly. Obviously I can't space it out too much, otherwise it'll flow off the end of the table, but there you go, a little bit of spacing can always help. Alright, so here we go. The screen on the bottom of the module can be scrolled through to obtain 12 characters, which are delimited by question marks, by, you know, this character. Use the following table, this character encoding is DOS code page 850, to convert these characters to binary. Call this the main code. Call this 90-bit binary value the main code. Was it 90? 12 times, oh, it's 12 times 8, so it's 96, yep. Call this 96-bit binary value the main code. Right, take the 7th to 48th bits from the main code. Group these into 6 rows of 7 bits, number the rows 1 to 6. Use the color of the top right LED in the following table to determine which rows need to be horizontally flipped and flip them. Then use the same table to determine whether or not to reverse the order of the rows. So instead of vertical in that table, I should say match cases on, that's why. Alright. Reverse rows. And I guess instead of horizontal, I'm just going to call it flip and reverse. Because the text already tells you exactly what flip and reverse means, right? It says horizontally flip, and it says reverse the order of the rows. The result specifies the vertical walls in a 7x7 maze. Take the 49th to 90th bits, group these into 7 rows of 6 bits. Number these rows 1 to 7. Use the same table above to determine which rows need horizontal flipping and whether, I forgot to specify that this time you need the bottom left LED. Use the same table above with the color of the bottom left LED to determine which rows need horizontal flipping and whether to reverse their order. The result specifies the horizontal walls of the same maze. Interweave the lines in such a way that the 7x7 maze is reconstructed. Note that the first horizontal wall of each row is horizontally in between the first and second vertical walls above and below it. Similarly, because the first horizontal wall obviously doesn't have a vertical wall above it. Tim, you do hate manual challenges though. I don't know why you say that. I love them if I get to decompile the code. I'm tremendously enjoying this right now. Let's see. Now where was I? I kind of lost my train of thought now. Right, yeah, that's right. Above and below. Right, note that the first horizontal wall of each row is horizontally in between the first and second vertical walls. There we go. I think that's good enough. Similarly, the first vertical wall of each column is between the first two. Yeah, that's correct. I should rephrase that. You don't like the way they are meant to be solved. Well, that depends on, I mean, it's up to the author of the manual challenge to determine how they are meant to be solved. You know, when I made Puzzword, I explicitly said everyone is welcome to decompile it, because I knew full well that that would be an even greater challenge than to figure it out, because it was designed to be figured out rather than decompiled. But this one here, I'm not sure if this is reasonable to figure out without decompiling. I don't know. especially given that it uses the super obscure code page 850, right? It doesn't use Unicode, it doesn't use standard Latin 1, it uses this antiquated DOS code page. Interweave the lines. Oh yeah, I was here. Right, I've read this, right? Similarly, the first vertical wall of each column is between the first two horizontal wall columns. No. That is confusing. Jesus. Note that the first horizontal wall of each row is horizontally in between the first and second vertical walls. Yes. Well, let's call those columns. Similarly, the first vertical wall of each column is in between the first two horizontal wall rows. There we go. Call the first 3 bits of the main code A and the next 3 bits B. Use the color of the top left LED in the following table to obtain your starting position in the maze. The first value is the 0-based x coordinate, the second is the 0-based y coordinate. A tilde means to negate the 3 bits. Use the last 6 bits of the main code in the same way to obtain your goal position in the maze. Navigate the maze. Oh, right, and the bottom right LED. Right, use the last 6 bits of the main code and the color of the bottom right LED in the same way. Use the last 6 bits of the main code and the color of the bottom right LED in the same way to obtain your goal position in the maze. Navigate the maze using the arrow buttons on the module. When you're on the goal position, press the green button with the target symbol to submit. The module is disarmed if the position is correct, otherwise a strike is incurred. The red button with an exclamation mark can be used to reset your position in the maze to the starting position. Right, I think we are done. I can space this out a little bit more. Yeah, I think this is good. So I think I'm happy with this. Now, obviously, this still needs an SVG. Can I be bothered to create an SVG? I think I can, because it would be incomplete without. So let's very quickly make such an SVG, and then we're done. Let's open component.svg, save this as ASCII Maze.svg, plonk that in here, put that at position 0, 0. I keep forgetting the size, 348, 348, there we go. Make it kind of transparent, I guess. There we go, let's make it even more transparent. Don't really need to see it all that detail. Right, I think I want to change the size so that it aligns with the... Right, that arrow there up there, that actually goes very close to the edge. So I think I'm gonna cheat and make it smaller, and it won't matter. Yeah, I think this is good. Let's center that. Right, now let's create a grid. Let's make it 10, 10, I guess. Oops. There we go. And then let's just draw something that vaguely resembles this arrow. I think I'm gonna go here. Yeah. All right, let's do this. Yeah, I think that looks reasonably similar. Let's give that a no filling and stroke paint of 2 pixels, I guess. There we go. And then let's take 1, 2, 3 copies of that, and let's put the center of rotation over here. So I need to decide where the LEDs are gonna go. So let's just quickly draw one of them. Oops, I want a circle. There we go. Let's make that fully opaque. Whoops, that needs a 100, not a 0. There we go. And now I'm going to take 1, 2, 3 copies of that as well, and then put the center of rotation. Yeah, that seems about right. Yeah, let's put it there. deselect one of these, and then rotate 90 degrees clockwise. Click. Deselect one of these, apply, one of these, apply, and then hopefully, yep, that is all of them. Okay, so we're gonna make this one here, yeah, in fact, I think I'm gonna make all of the LEDs some shade of gray, like this maybe. Right, so let's make one of them very bright, one of them less so, one of them even less so, and one of them very dark, because blue is obviously the darkest color. And then let's draw the buttons there. Right, this one here is the green quote-unquote target button. So I can do that. Again, I don't, you know what, I'm just gonna copy this. There you go. That goes there. And now let's just draw a little circle. I need 2 circles. It just needs 2 circles. Okay. So let's do that and make it 50%, I guess. Blank. Yeah, I think it could be a bit more. 60%. Right, and then the other one should probably be half the size, so 30%. Yep, that looks good. Okay, and then we copy this over, put that here. Let's see. All right, the tip of that button here is below the tip of that arrow, so I'm gonna do the same thing here, and then I'm gonna put an exclamation point here, but maybe in a reasonable font, like maybe a Work Sans, size 24, maybe a bit bigger, 32, maybe a bit bigger, 48, maybe a bit smaller, 42. Alright, let's turn that into a path, and then make that horizontally and vertically centered. There we go, save that. And finally, right, we have an arrow button here. Okay, I think I want the grid to be a bit finer for this one. Let's put that here, and then here, and then here, I think. Is that symmetric? I'm suddenly not sure if this is symmetric. Right, if I vertically flip this, if I vertically flip this, there's no, see, horizontally flipping works, right? So if there's no visible change when it's vertically flipped, then it means it's symmetric. All right, and that one goes there. Let's also align that with the button, and then put a square here. Well, not a square, a rectangle. That is 3 grid points away, and that's good enough. I think I'm going to fill this one with black and no stroke, and then remove the background. Right, I think that looks pretty good. Wouldn't you say? I think I also want to, because these buttons have this sort of thick side, I think I want to do that too. So I'm going to, here's what I'm going to do. I'm going to duplicate these and then union them, so it's one single thing. And then I'm going to draw a rectangle around here, like this, and then I'm going to use the intersection of those. Okay, and this one I can fill, no stroke, and that is exactly how I wanted it. Now let's do the same thing here, duplicate that. Whoop, I should probably just select both of them and then duplicate and then union, and then do this, like that. And then, what was the shortcut for intersection? It's Control-Shift-8. There we go, and then no stroke, fill. Perfect, I love that. Okay. With that, I think we are done. Right, let me also select everything except for the status light and the outline, group it, and then center it on the page. So I want to center it like that, like that. Okay, that's probably a bit more professional. And now ungroup everything and save that. That looks amazing. Thank you very much, Tracks Josh. Welcome to the stream. Oh, you have written something before, so I just didn't notice you. I do apologize. Yeah. Okay, that does look just like the module. So let's close that. Let's also go here and open it here. ASCII Maze. Let's paste that here. And bang, it's now very, very small. And now let's use my regular expression to make it even smaller. And then let's use another round of this and make it even smaller. Okay, we definitely don't need this. We definitely don't need this. We definitely don't need this. And I think that should be it. Right, let's see if that can be reduced. Yes, it can be reduced even further. Alright, oh, fill rule even odd. We don't need that either. And you know what? Stroke width 2, we probably don't need to specify that everywhere either. We can just specify that as a single default, and then the whole thing will just have that as a default. And there we go. Now it's super mega small. Alright, with that out of the way, we can close this. And now if I go here and refresh this, we have that SVG in the corner. Alright. Manual challenge done. Ooh, I just realized, ooh, look at this. There is a space. The space doesn't show up. So I'm going to cheat here. I'm going to check out where in this table that is. And I'm going to cheat and actually put a non-breaking space there just to align this properly. But obviously on the module it'll look like an empty space, so that's fine. Okay. So now I notice that the special elite font doesn't actually have all of these characters. You know, all of the accented characters. Maybe I should try and find a new font for that, especially given that, I mean, if you look at this here, this doesn't look the same way as it does in the module. I wonder what the font that the module uses is actually called. Let's go back to ASCII Maze on the Steam Workshop. And let's see, it only shows that, there is something, okay. No, that is clearly too small to recognize the font. Right, so I think I'm going to use the Trebuchet font. Because I think Trebuchet has all of these characters. I just noticed that, I should have realized that some of these characters require HTML escaping. Less than character, greater than character. Right, so I think I'm going to use the Trebuchet font. So in the .codes table, I'm going to say font family Trebuchet MS, I think it is called. And that is quite a bit more readable. And also more consistent. Right, these now have the same font as these. Okay, and the 3/4 looks closer to what it should. Yeah, I think I'm reasonably happy with this. Right, let's leave it like that, shall we? So the reason I'm confident that the Trebuchet font will work is because on the repo we have this font.css file, and it defines quite a lot of fonts, including Trebuchet MS, because that is used by the main page on the repo. Right, so the same CSS file, which is used by all of the manuals as well as the front page, has Trebuchet in it defined in it. So with that, I'm now going to call this complete and done. So thank you very much for watching, and I hope that you will enjoy this module as much as I did decoding it. And I will see you again the next time when we have a manual challenge, or maybe some more souvenir support for tomorrow. If you have any suggestions for new modules that I could add souvenir support to, then tune in tomorrow and message me in the chat. And until then, thank you again for watching, have a nice day, and I will see you again. Goodbye.